Hello, everyone, and happy Geography Awareness Week. On behalf of all of us at the American Geographical Society, welcome to our annual Fall Symposium. For the past symposiums, we've gathered here at the Roone Arledge Auditorium at Columbia University for our annual event. Every year, we get together, renew our friendships, participate in intensive geo conversations, exchange ideas, and hear from world-class geographers, geospatial scientists, innovators, and other fascinating speakers, all of whom are leading the way to address the issues facing our planet. This meeting has become one of the most important geo events in North America in the fall, and this pandemic has certainly challenged us to be able to continue these very important discussions and tradition. This room is so quiet and lifeless without all of you here. But the good news is that we are planning to meet here again next year, and in the meantime, we are welcoming thousands of you from around the world to join us digitally today and over the next few days for what we think is going to be a great week. We have replaced the stage behind me with a digital stage, our specially designed website, which actually is going to host far more events than we usually do here. I invite you to join us every day this week for panel sessions, lightning talks, spotlight presentations, special plenaries, book reviews, and interviews. You can even test your geo knowledge daily with a short, fun quiz aligned with the theme of the day. Look, it's not the same as all of us together here, and I don't want to pretend it is. But I can tell you that the lineup of speakers and the willingness of our presenters to be a part of this event in spite of less than perfect accommodations is really a testament to the importance of the discussions we are all having, be it face-to-face or using technology to bring us together from around the world. So welcome. We're looking forward to spending the week, our week, Geography Awareness Week, with all of you. And now, it gives me great pleasure to introduce the chairman of the American Geographical Society, Dr. Chris Tucker, and our president, Dr. Marie Price. Chris and Marie.
Thank you, John. Welcome to Geography 2050 with its theme, The Future of the World Ocean. For months now, we've been planning our first virtual conference, and we are so excited to share our efforts with you this week. While I don't think it will replace the fun of gathering in New York City each November, we are delighted that so many more people from all around the world are able to join us this week. The American Geographical Society began in New York City in 1851. We are the oldest national geographical organization in the country. The founders of AGS were inspired to explore, map, and record changes on the Earth's surface. Yet the society was always engaged in vital environmental, social, and economic questions in an effort to use a geographical perspective to answer these challenges. One of the ways we do this is by convening people from academia, government, industry, and civil society. We believe in the power of people speaking to each other, not at each other, across these sectors. Geography 2050 embodies this philosophy. We could not do this work without the help of the AGS Council, our governing body, whose members come from different sectors but are united in their love and appreciation for geography as a way of understanding and transforming the world for the better. And of course, we are fortunate to have dedicated staff members and interns who turn these ideas into reality. Geography has experienced a resurgence in the US, especially with the popularity of AP Human Geography in high schools across the country. We welcome the AP Human Geography teachers who are attending today and their students. In the past years, 50 AP Human Geography teacher fellows would join us in New York City to attend the conference and a special workshop afterwards. This year, hundreds of teachers are joining us remotely, and we will have a special workshop for you on Saturday, led by Dr. Lisa Benton-Short, a friend of AGS and chief reader for AP Human Geography. So please sign up for this workshop. In order to make this event possible, we are especially grateful to our corporate angels, companies that believe in the power of geography and geospatial tools to change lives for the better. In particular, I want to acknowledge Arturo, Critigen, Dean Wise LLC, Dewberry, FSI, GeoCisu, Mantech International, TeachOSM, 10X Aerospace, and Voyager. This year we are making Geography 2050 available free of charge. As you will see, there is a tremendous amount of work and expense to put this event on. If you like what you see and learn today and throughout the week, please consider making a donation. Any amount is welcome, and it can be done with a click of your mouse. And with that, I pass the microphone to my colleague and chair of AGS, Dr. Chris Tucker.
Thanks, Marie. I'd like to join you first in underscoring the importance of the work of our illustrious leader, AGS CEO, Dr. John Konarski, and our amazing staff in helping us transform this event into our first virtual Geography 2050. Of course, beyond their hard work and that of our council, these events would not be possible this year without the leadership of our two program co-chairs, Dr. Lawson Brigham of the University of Alaska Fairbanks and Dr. Christopher Linden of Applied Ocean Sciences. These two leaders, both officers in the U.S. Coast Guard and PhD oceanographers, have a passion for the role of geography in understanding our oceans and the role of our oceans in supporting our planet and our species. So thank you to them for the countless hours of hard work and their willingness to share their Rolodex, their connections with an amazing network of experts who you will get to witness as part of this week's event. This event also would not be possible without our long-term partners. Normally, this event, as Marie said, would be held in New York City at Columbia University, sponsored by the Columbia Earth Institute. Their support over the years has meant everything to this event, and we are happy to have them partners on this first virtual event. And hopefully we look forward to being back in New York sometime after the pandemic ends. We'd also like to thank the Fund for the City of New York, U.S. Geospatial Intelligence Foundation, and the Open Geospatial Consortium for their long-term partnership in this multi-year strategic dialogue about the vital trends that will reshape the geography of our planet over the coming decades. Additionally, we're lucky to have our sponsors. We have our premium sponsors in Black Cape, ESRI, Maxar, and Reinventing Geospatial, known as RGI. Also, we have our sponsors, the American Association of Geographers, Applied Ocean Sciences, Symposium, Crunchy Data, Impact Observatory, MapStory, National Geographic, the Open Sensor Hub team, Rutledge, and their label, Taylor and Francis, and Wolpert. Thank you so much to all of you for sponsoring this event. Without you, it simply wouldn't be possible. Beyond that, this year we have someone new to thank because going virtual is actually a huge lift and a gigantic challenge. And without Adam Simmons from Project Geospatial and all of his expertise in helping us go virtual, we would never have been able to transform this in such a short period of time into such an amazing week-long celebration of the oceans. I encourage all of you to check out projectgeospatial.com in your spare time for all sorts of great content around about the geospatial industry, technology, innovations, and the challenges that the industry faces. So thank you to Adam. And with that, I'd like to introduce our two program co-chairs for this year, who I've already introduced, Dr. Lawson Brigham and Dr. Christopher Linden.
Thank you, Chris. Welcome, everyone. I'm here to set the stage for the AGS Geography 2050 Symposium, Future of the World Ocean. I'm Lawson Brigham, co-chair of the symposium with my colleague, Christopher Linden. Both of us are oceanographers and have sailed extensively at sea as U.S. Coast Guard officers, so we're both connected to the ocean in many ways. The future of the planet is certainly linked to the global ocean. Planet's warming, and so are all of the oceans. The oceans are changing in profound ways, and their health should be of concern to all humanity. As we have said on our website, the oceans in the 21st century are many things to many people. They're a highway for trade and economic growth. We certainly rely on global fisheries. The oceans are a geostrategic space where navies and merchant ships operate. And sadly, the place is a region of the planet for pollution and dumping. The oceans also, over history, have provided inspiration to generations throughout all time. All of these uses and perspectives of the ocean today are under great change. The oceans themselves, once thought as inexhaustible, are under great stress. So in this symposium, we're hoping to provide you with a basic understanding of the complexity of all of these changes, all profound, and all impacting people not only along the coast, but throughout all of the deep oceans. In the next 5 days, we have a comprehensive program based on 5 themes, and I'll go down the list. You can see them on our website. The first day, today, we have human impacts on the oceans, a special plenary, which Chris in a moment will speak to. The second day, oceans as a contested environment. We have experts and some naval officers to speak about the complexities of law enforcement and naval protection around the world's oceans. Third day, a special day with explorers, is titled Exploring, Mapping, and Sensing the Oceans. On the fourth day, our sessions speak to the bounty of the oceans and protecting this place, our place. And then finally, on the fifth day, which I'm involved with in chairing a session, is the changing boundary between human habitats and the sea, and we'll speak to the Arctic and also the coastal zone. So I'll turn this over to Chris now, and he can speak to our special plenary and some other aspects of this week. Chris?
Thank you very much, Lawson. My name is Chris Verlinden. I'm the CTO of Applied Ocean Sciences, and I'm honored to be co-chairing this week's event with Dr. Brigham. Before I was the CTO of Applied Ocean Sciences, I was a Coast Guard officer, and I spent much of that time working on icebreakers in the Arctic, being weaned on stories of adventure and intrigue from Dr. Brigham's earlier career. It's an absolute pleasure and an honor to be co-chairing this event with you, sir. After I spent my time in the Arctic, I taught GIS at the Coast Guard Academy for a few years, which is how I was first introduced into this wonderful geography community. This event to me is very special because it represents a fusion of these two worlds, my two worlds, the geo with the ocean, the oceanography. And this is appropriate, I think, because 70% of our planet is covered in ocean. We really do live on a blue marble. This week, we'll be discussing the future of the world ocean in terms of the 5 distinct topics that Dr. Brigham mentioned. There's a number of different ways you can choose to participate in this event. First of all, you can tune in live every day on the geography2050.org website, each day starting at 9 o'clock Eastern Time. And you will see all of the live sessions for that day's events showing in order as listed on the schedule. If you aren't able to watch the day's event consecutively in real time, you can navigate to the Vault. So if you click on the Vault link on the geography2050.org website, you can choose any individual session you'd like to watch or share with your friends, students, colleagues, etc. There's a variety of different ways you can interact with all these topics, and we believe it'll be very interesting and informative to educators, policymakers, scientists, and anybody interested in the future of the world ocean. Now, one of the reasons this topic is so interesting to me, like I said, is because I've always been a bridge between the geo and the oceanography community. And something that used to interest me, but before I found the answer, was why we call oceanography oceanography. I always thought it should be called oceanology. That makes more sense to me because it seems to follow the convention of other disciplines. Well, it turns out that one of the reasons we call oceanography oceanography is because we used to describe the field of studying the ocean as mapping the largely static parameters or qualities of the ocean. But we now know that that's not entirely true. The ocean changes a lot, and on timescales ranging from hours to days, weeks, months, years, decades, and centuries. And we are currently experiencing a period of unprecedented changes in our oceans, which is why the subject of our first special plenary session is the top 10 greatest challenges facing the world ocean. We'll discuss topics ranging from acidification to warming, sea ice loss to plastics, and we'll be discussing what the future of the world ocean looks like and what you can do about it. The ocean that we see in 2050 and that our kids see in 2100 will likely not resemble the ocean that we see today, and not for the better. And that's why today's topic is human impacts on the ocean.
And who would have guessed, Chris, that we all were reading every day about plastics spreading throughout the whole of the global ocean? Science tells us that we see plastics in the Arctic Ocean, down in the Southern Ocean, and plastics were found in the Challenger Deep, the deepest part of the ocean. Remarkable. Impact.
People are even starting to call our era the Plasticine, because our impact, our legacy in the fossil record will likely be a layer of plastics everywhere.
Extraordinary impacts.
Yeah. Absolutely extraordinary. So let's discuss some of these impacts more. Without further ado, I'd like to move to our very first session, the top 10 greatest challenges facing the world oceans, where we'll discuss ocean plastics and a variety of other topics.
Welcome to the special plenary session, the top 10 greatest challenges facing the world ocean. I'm your host, Dr. Christopher Linden, oceanographer and co-chair of this year's GEO 2050 event. Today we will be discussing 10 topics of concern for the world ocean, 10 ways in which the ocean is changing, and not for the better. But there is hope, and we will also be talking about what you can do about every single one of these topics. The 10 topics of concern today are ocean acidification, global ocean warming, sea level rise, sea ice loss, coral reef loss, ocean deoxygenation, mangrove deforestation, ocean plastics, ocean noise, and overfishing. 9 of the world's leading experts in their respective disciplines and I will be discussing each of these 10 challenging issues. My colleagues here today represent leading international experts and exciting rising stars in the community. I will be starting off today's session by discussing a topic that is near and dear to my heart. I wrote a paper a few years ago discussing a proposed method of remote sensing of ocean pH using acoustics. And the next topic was my primary motivation. Ocean acidification is one of the most fundamental and straightforward topics we will be discussing today. Now, in order to understand ocean acidification, we need to first talk about what is meant by the term acidification. Not surprisingly, the term acidification refers to when a fluid, in this case the ocean, becomes more acidic. But what is meant by the term acidic? Well, acidity is typically measured on the pH scale, which ranges from 0 at the most acidic to 7, which is neutral, and 14 at the most basic end of the scale. To put it in terms of household chemicals, which you might understand and be familiar with, vinegar, a common household chemical, has a pH of 2.5. And since that 2.5 is lower than 7, lower than neutral, that means it is very acidic. Sulfuric acid, which you might have heard about in high school chemistry classes or even used, has a pH of 2.75. On the other end of the spectrum, we have baking soda or sodium bicarbonate, which has a pH of about 8.3. And again, since that 8.3 is higher than 7 or greater than neutral, that is a basic chemical. Milk of magnesia or magnesium hydroxide has a pH of a whopping 10.5, making it extremely basic. Now that we understand the term acidification and what is meant by acidity, we need to talk a little bit about how and why the ocean is becoming more acidic. Well, it's fairly straightforward. The cars we drive in, the planes we fly in, and the power plants that produce our electricity all produce carbon dioxide as a byproduct of the combustion reaction which fuels these cycles. And that carbon dioxide then spreads around the world ocean and comes in contact with seawater everywhere. And when carbon dioxide comes in contact with seawater, it dissociates into carbonic acid and bicarbonate and free hydrogen ions. Now, the definition of pH that we didn't discuss earlier, the strictly mathematical definition, is the inverse logarithm of the concentration of free hydrogen ions in the fluid. So what that means is if we increase the level of free hydrogen ions, we make the fluid more acidic, dropping the pH. So as we produce carbon dioxide, that carbon dioxide interacts with the ocean, dissociates into carbonic acid, which as the name suggests is acidic, which raises the concentration of free hydrogen ions, thereby decreasing the pH of the ocean, making it more acidic, and overall a less comfortable home for marine organisms that rely on a fairly basic or neutral ocean for their well-being. You don't need to take my word for any of this. Today we're going to do a very brief demonstration in the laboratory of ocean acidification, starting with a combustion engine, exposing seawater to that combustion engine, and watching what happens, watching the pH drop. Thank you very much. So we're going to start off with a sample of seawater right here. I am going to pour the seawater into 2 equal sample vessels. So you can see that both of these samples of water come from the same source and have the same initial pH. I'm going to measure the pH using this pH sensor, where this probe is inserted into the water, and on this screen, which we'll zoom into, you can see the pH of the fluid. So I'm going to insert the probe into the water right here and measure the pH. And if you zoom in, you should be able to see that the pH is a little over 7. Now it's dropping a bit, and I bet it will actually equilibrate out to just under 7, but the water that comes out of your tap is fairly neutral. Now what we're going to do is we're going to inject water into one of these, CO2, into one of these 2 sample vessels, and we're going to measure the pH as we do that. Now if you want to do this at home, let's say over Thanksgiving with your family, you could use something a little bit less expensive, and these pH test strips used for pools or hot tubs will work just as well for your purposes. Now in order to get CO2, you can blow bubbles into the water with a hose. That's not very much fun. It doesn't really illustrate the internal combustion part of this whole problem. So I'm going to use this highly scientific leaf blower here. Now remember, you might not want to try this part of it at home because I am a professional physicist, but still counts. So I'm going to start up my CO2 generator here, my highly scientific device. So you can see if you zoom in that just by running it for a few seconds, we were able to drop the pH to about a 6.5. We probably could have gotten it a little bit lower if we ran it for longer. Just to show you that it's not a trick, we will dip the pH sensor in that original sample of water, which remember came from the same sample vessel, and you'll see the pH on the sensor rapidly increase to closer to 7, back to neutral. So you can see that by running a combustion engine, which produces carbon dioxide just like your car, just like the planes we fly in, just like a power plant, and exposing seawater to that CO2, we were able to drop the pH, and in this case to a level that would be difficult to survive for many marine organisms. Thank you very much for that demonstration. You can see that that was done in my basement. The demonstration that we just saw showed the acidification process from a combustion engine to producing carbon dioxide, lowering the pH of a fluid, causing it to become more acidic. So we now understand the chemistry behind ocean acidification. Now we need to get a handle on the scope and scale of the problem in the current state of ocean acidification in the world ocean. Well, as you can see from this chart, a plot of ocean pH and CO2. On the y-axis on the left side is concentration in parts per million of CO2 in the global world atmosphere. And on the right-hand side is the average sea surface pH across the world ocean. So you can see between 1960 and 2010, the concentration of CO2 in the atmosphere due to the anthropogenic production of CO2 has raised from 300 parts per million to nearly 400 parts per million. And over the last 20 years of that same time period, the average surface pH of the ocean has dropped from about an 8.1, which is fairly basic, to an 8.05, which is still basic, but less basic. And that represents a very significant change because remember, pH is a logarithmic measure. So 0.05 is significant. And what's more significant is if we carry those trends forward to 2100, you can see by the red line in this plot that it is anticipated that by 2100, the global average sea surface pH will decrease to 7.8 if we do nothing to change our current output of carbon dioxide. There is, however, a silver lining to this cloud because from what you can see on the blue line, if we curb our CO2 emissions significantly, then we can stop and even reverse this trend, increasing the sea surface pH back to natural levels. Now, in order to see this more visually, I want to show you this plot of global sea surface average pH in 1850. Now, this is estimated because we didn't have all the same measurement instruments, but I want you to see that the average ocean pH at the surface is well over 8. It's very basic. And this map is dominated by dark blue colors. And there's a little bit of light blue and certainly nothing going into the yellow on this particular color bar. Now, if we advance to today's ocean pH, we can see that the ocean is still largely basic, but less so. The average pH you can see is still just a little bit over 8, but only a little bit. And it's not a uniform distribution. The Pacific Ocean tends to be a little bit more acidic than the Atlantic Ocean, for example. And that's not necessarily of concern, because organisms that have evolved to live in these locations have evolved to live under these current acidity conditions, and that's okay. But now, if we look at the anomaly, which helps us understand what the trend in ocean pH is, it's a lot more concerning. The ocean pH anomaly, represented here in this plot, shows what would happen if we subtracted our current ocean pH from the average pH over the last 200 years, representing the pH difference between now and what has been the average over this period. And if we look at the anomaly, we can see that everywhere on this plot, the anomaly is negative, which means everywhere in the world ocean, the pH of the ocean is decreasing, meaning the ocean is becoming more acidic. And again, not uniformly. If we look at these red and orange numbers in the North Atlantic, the ocean pH in these areas has dropped by 0.12. On a logarithmic measure, this is an extremely concerning trend. And if we carry that trend forward, as you can see here in this plot, and show what the ocean sea surface average pH is expected to be in 2100, contrast this with the plot we saw a few slides ago of a dark blue, basic ocean everywhere. We see this ocean is almost entirely light blue and even yellow, meaning the ocean is going from being extremely basic to almost neutral. And you might ask yourself, why does that matter? Neutral sounds okay. And on the surface, you're correct. But as is probably not surprising to you at this point, the chemistry of how biological reactions that marine organisms count on to survive has evolved over the millennia is for the current ocean conditions. And this is perhaps best represented by a measure called the aragonite saturation state, which you can see from this equation is basically the concentration of free calcium and carbonate ions divided by their equilibrium concentration. And what that essentially means is it represents a bioavailability of this type of calcium carbonate for chemical reactions such as organisms building their calcium carbonate shells or tests. They're building their homes. And so what you can see based on this plot of the aragonite saturation state in 1850 is that the vast majority of the ocean has a fairly positive aragonite saturation state on the order of 3. That means organisms can build calcium carbonate shells in the vast majority of the ocean. Now, if we continue the pH trend that we saw on the previous charts forward and look at the aragonite saturation state projected in 2100, we can see these massive regions of the world ocean which are orange and even red, which are areas where organisms would have a difficult time forming calcium carbonate shells and therefore would be unable to survive. So in short, what this plot is showing is that by 2100, significant portions of our ocean will be uninhabitable to a significant number of marine species. So who cares? You're not a marine species. Well, for starters, salmon care, and anyone and anything that eats salmon, from a grizzly bear to human beings. Now, the reason that salmon care about ocean acidification is that salmon are what's called an anadromous fish species, which means they spend some of their time in rivers and some of their time in the ocean. And when they're in the ocean, they love to eat these little critters called pteropods. Now, pteropods are a pelagic, meaning they live in the water column, free floating, not on the bottom or not on the surface. They're a pelagic snail species, which, as you've probably guessed by now, form calcium carbonate shells. And, as you've probably also guessed by now, if the ocean continues to become acidic at its current rates, they will be unable to form those shells in the future. They are one of those species I mentioned that will not be able to survive if the ocean keeps becoming as acidic as it is. So this will have what's called a trophic cascade, which means if there are no pteropods, the salmon that eat the pteropods will be impacted. And then all the organisms that rely on the salmon, including grizzly bears and ultimately human beings, will also be impacted. So, in short, everyone cares. Everyone who in any way is associated with this food chain, which is all of us. So at this point, you might be asking yourself, what can I do? The fact is, all of these trends are extremely concerning. And you might be asking yourself, what can I do as an individual, as a private citizen about this problem? Well, there's at least 4 things. The first thing you can do is support scientific research. What I mean by that is when there's a ballot on the election that says, should I increase funding or decrease funding for oceanographic research, particularly marine chemistry? The answer really needs to be increase at this point. The fact is we need to understand this problem better. We need better sensors that can measure the pH of the ocean in situ. We need remote sensing technologies that can measure pH all over the world ocean so we can understand the current state of the problem and make more accurate predictions about the future so that we can be prepared for what the future of the world ocean holds. Second, support initiatives to empower women in demographics that are underrepresented in the scientific community. Now, it's not always immediately clear what the links are between some of these socioeconomic and often politicized issues and a scientific topic like ocean acidification are. But it's been shown by statistics that a more prosperous community that has more educated individuals has more minds working on solving a problem like this, and that is always a good thing. In short, support initiatives to empower women globally and underrepresented minorities in the scientific community. Third, reduce your personal carbon footprint. Now, I am not an expert in this particular portion of climate science, but I interviewed a lot of experts in preparing for this talk, and some of these things are very simple. You can drive less and take public transportation more. Eat less or even no red meat. Eat a plant-rich diet. Get solar panels for your house. Reduce your food waste. Fly less, and maybe buy carbon offsets when you do fly. Minimize new product purchases, or insist through your purchasing power on sustainable supply chain management in the things that you do buy. And maybe reduce your house temperature a little bit in the winter and increase it in the summer to reduce the amount of electricity and power that you use, among a great many other things. Finally, communicate about climate change. Many of you in the audience might be professional educators, in which case, educate. If you are not a professional educator, educate. Talk to your friends, talk to your family. Maybe bring up the uncomfortable topic of ocean acidification over Thanksgiving dinner. Because the fact is, those of us who understand the problem, which now includes you, have an obligation to do something about it. And one of the most impactful things we can do is to start a conversation and open a dialogue between everyone who will listen, which for all of us includes our inner circles, our friends, and our families. So in conclusion, support scientific research, support initiatives to empower women and demographics underrepresented in the scientific community, reduce your personal carbon footprint, and communicate about climate change. Thank you very much. Like I said, ocean acidification is one of the most fundamental topics discussed here today because it is a direct consequence of the CO2 that we as people put into the atmosphere. Similarly, our next topic, presented by Dr. Greg Sennett, global ocean warming is a result of anthropogenic input of CO2 into the atmosphere. Dr. Greg Sennett is a postdoctoral researcher at the University of California, Irvine. An observational physical oceanographer, he studies processes affecting nearshore circulation, mixing, and stratification. As part of his research as an AAUS science diver, Dr. Sennett often uses equipment deployed in the dynamic nearshore environment to measure heat flux, internal wave dynamics, and other nearshore processes, with direct implications for coastal ecosystems. As an NSF fellow, Dr. Sennett has also developed high school earth science curricula focused on experimental learning techniques and making pioneering research accessible to and exciting for beginning scientists. Dr. Sennett earned a PhD from Scripps Institution of Oceanography in 2018 and holds MS and BS degrees from the University of Maine in oceanography and engineering physics. Thank you very much for being here today, Dr. Sennett.
Okay, thank you, and hello everyone. My name is Greg Sennett. I'm a postdoctoral researcher at the University of California, Irvine, where I primarily study coastal ocean processes. One of the ways that I do that is by measuring ocean temperature in ways that inform us about water mixing, transport, and other important physical aspects. Ocean warming is a significant challenge, so in the next few minutes, I'll try to briefly summarize the problem and then highlight some of the research and implications related to global ocean warming. By now, you're probably well aware of the factors that contribute to climate change, but if not, I'd encourage you to explore the Intergovernmental Panel on Climate Change, or IPCC, reports, which are an excellent source of accessible and extensively peer-reviewed climate and ocean science. One aspect of climate change that I find frequently surprises people is that the ocean has taken up more than 90% of the excess anthropogenic heat of the climate system. On the face of it, this may seem like a good thing, leading to less atmospheric heating, but as we'll see, that's not the case. These two plots from the IPCC Fifth Assessment Report summarize how the global ocean is warming. The plot on the left shows the evolution of globally average temperature difference from the mean of the top 700 meters of the ocean. And the map on the right shows the temperature trend of the top 700 meters over the same period. The IPCC, in conjunction with thousands of scientists around the world, conclude with certainty that the surface ocean is warming. And it's fair to ask how we know this, so let's explore some of the research behind this conclusion. Ocean temperature observations date back a very long time. Coastal observatories, ocean moorings, ship, and more recently, autonomous glider transects all record data at various locations and over a wide variety of depths. The observed ocean area vastly expanded in 1979 when satellites began to observe sea surface temperature. Modern satellites fly in coordinated orbits, making a wide variety of observations from the top of the atmosphere down to the surface of the ocean. And these data are publicly available, and I'd encourage you to go check them out. For example, a recent global sea surface temperature observation from the MODIS Observatory on the Aqua satellite is in the lower right. Satellites observe only the surface ocean, however, and observations in deeper water are sparse, which is why the Argo program was initiated and has become so important. Since 2000, Argo floats have provided continuous observations of the ocean's top 2,000 meters. And as of a month ago, there were nearly 4,000 operational floats deployed by 24 different countries throughout the world. These data are also publicly available. So here's a plot from an instrument that I pulled at random, not too far away from where I am now. This plot shows depth on the y-axis plotted versus temperature, and it clearly shows the classic ocean temperature profile with warm, less dense water floating near the surface and cooler, denser water below. Of course, these data can be used to study many different processes, but how are all these measurements used to study global ocean warming? From a global ocean warming perspective, scientists are basically trying to understand three fundamental things. And that's, what is the heat flux through the ocean surface, both into and out of the ocean? How much heat is contained near the ocean surface? And at what rate is surface ocean heat mixed into the deep ocean? And these are three really important questions. The first question addresses how much heat is entering or leaving the ocean system. The second question addresses the temperature and habitability for organisms in the epipelagic or sunlight zone, where most of the ocean's biomass is contained. And the third addresses the rate at which the entire ocean heat content is changing. So let's now talk about a few implications for a warming ocean. Sea level rise is a direct consequence of the rising ocean temperature. As water temperature rises, the volume that water occupies increases related to the thermal expansion coefficient. And you can actually explore this and determine the thermal expansion coefficient for yourself. One experiment that I like is linked at the bottom. Sea level rise is a topic of another talk, so I won't say too much more about it other than to point out that thermal expansion is a significant contributor to the observed global mean sea level rise. Another direct implication of global ocean warming is increased stratification. As the surface ocean warms, the surface layer becomes less dense, and the ocean becomes more stratified or harder to mix. Intensified surface warming has increased thermal stratification of the surface ocean by about 4%. And this map indicates the rate of stratification change around the world. Increasing stratification and the subsequent reduction in mixing is troubling since oxygen-rich near-surface waters are less likely to be mixed downward, and similarly, nutrient-rich deeper water can't be mixed to the surface photic zone where primary production can occur. Thus, increasing stratification is very likely to reduce primary productivity and fish stocks, according to the IPCC. And again, there are several experiments that you can try yourself to see how increasing stratification inhibits mixing. This is an experiment from the University of Maine that I particularly like. Marine heat waves are defined in a few different ways, but are essentially prolonged periods of abnormally warm water, partly due to the increased stratification and partly because of the extra heat in the climate-ocean system. Marine heat waves have doubled in frequency, become longer lasting, more intense, and more extensive. The IPCC concludes that 84 to 90% of the marine heat wave events occurring between 2006 and 2015 were due to anthropogenic temperature increase. Here, the plot on the left highlights some of the more recent marine heat wave events and their attributable costs. Like ocean temperature in general, marine heat waves have far-reaching effects, even causing droughts, floods, intensified storms over land, in addition to the direct ocean ecosystem impacts. And you can monitor marine heat wave conditions on your own. For example, this map shows conditions recently on November 5th. Finally, let's look at how the global ocean temperature is expected to affect a wide range of ocean ecosystems. The plot here in the upper left panel shows the global mean sea surface temperature versus time. The brown line is the observed temperature with the current warming level above pre-industrial temperature shown by the horizontal gray line. The red and blue lines represent predicted temperature under two different climate mitigation scenarios. The red line is the predicted sea surface temperature under a business as usual scenario, basically doing nothing. The blue line represents the predicted sea surface temperature with aggressive climate change mitigation measures in place. The remaining colored bars here represent the degree to which ocean warming affects various ecosystems, with white representing undetectable effects and healthy ecosystems, and purple representing a very high ecological risk. So today, we're documenting adverse effects to the epipelagic, salt marsh, seagrass, kelp, and warm water coral ecosystems with high or very high confidence. But in just 30 years, at our current level of warming, all ecosystems, including the deepest parts of the ocean abyss, will likely be affected, with the most biologically productive and diverse ecosystems affected at high or very high levels. So that's just a very brief tour of the global ocean warming problem and some of the science behind it. The problem, like any potential solution, is complex, it's far-reaching, it's tied to climate change with impacts to global economies. And if there's any silver lining to anthropogenic climate change and global warming, global ocean warming, it's that it's anthropogenic. We changed it so we can affect change. And I've left this plot up to emphasize that point. There are personal choices that we can make to help mitigate both atmospheric and ocean warming, from eating lower on the food chain to simply being aware of and reducing how much energy and material we consume. We can also prepare for expected changes, such as sea level rise. And importantly, I want to emphasize that it's individuals who first spark systemic change, and that has real potential to move the climate needle. And ultimately, climate mitigation will involve governments, industry, and individuals, but science needs a seat at that table. And all of us can be an advocate for evidence-based science. The IPCC reports are a great place to start if you're new to the topic, and I encourage you to go check them out. I hope you found this talk helpful, and as you listen to others related to climate science and ocean science, I hope you'll continue to think about how you can take action. Thanks.
Thank you very much, Dr. Sinnott, for that informative talk on global ocean warming. The next topic we'll be discussing today is closely related. It's sea level rise with Dr. Gino Passalacqua. Dr. Passalacqua is an oceanographer, meteorologist, and fisheries scientist. He is currently a scientific advisor for the Save the Wave Foundation. Previously, he was a marine technician at UC San Diego and worked on board for the Scripps Institution of Oceanography Ships of Opportunity program. Before that, he worked as an associate technician at Universidad Autónoma de Baja California, where he implemented and developed a coupling system between WRF and the Regional Ocean Modeling System, or ROMS, for the study of air-sea interactions of winter cold fronts in the Gulf of Mexico as part of a research team for the CICESE, Petróleos Mexicanos, PEMEX project, mooring network in the deep Gulf of Mexico. His PhD studies looked at air-sea interactions of winter cold fronts over the warm waters of the Gulf of Mexico, analyzing momentum, heat flux, and moisture fluxes using the Weather Research and Forecasting, or WRF, model as a diagnostic tool. Dr. Passalacqua has been a good friend, colleague, and collaborator of mine for over a decade, and I very much appreciate him being here. Thank you very much, Dr. Passalacqua.
Hello, my name is Gino Passalacqua. I'm a committee member of the Bahia de Todos Santos World Surfing Reserve and a scientific advisor for Save the Wave Coalition. And today I'm going to talk about sea level rise, implications for coastal conservation, and surf ecosystems. As it is well known by now, sea level has risen between 21 and 24 centimeters since 1880. As you can see from this map that you're looking at, the sea level change is not homogenic around the world. There are some areas that have higher sea level change, and there are some areas that have even a decrease in sea level change, mainly around Antarctica. How this translates for coastal environments? For example, in the U.S. coastline, high tide flooding is now 300 to more than 900% more frequent than it was 50 years ago. And 2019 was the highest annual average sea level change in the satellite record. So we know that sea level is increasing, and there's some different factors that contribute to this. In early this year, Frederiksen and all published a paper where they look into these different factors. From the 1900 to 1940, it was mountain glaciers and Greenland ice sheets, the main contributors. During the 70s, there was a decrease in this upward trend due to global dam projects. Basically, there was less water flowing to the ocean from the rivers. And since the satellite era, the main contributors has been the Greenland and Antarctic ice sheets melting, thermal expansion of the oceans, and mountain glaciers melting. So how do we measure this? These different factors, contributing factors. We use tidal gauges around the world, as you can see on the map. We use ground stations. We use satellite data with radar altimetry, gravimetry, and laser measurements. You can see on this map the orbit of Jason 3, which is one of the satellites that measures radar altimetry. So we talk about different factors contributing. The main factors since the satellite record are atmospheric height and ocean mass. So since we have these satellite records, there's been an average rate increase of 3.3 millimeter per year. The steric height contribution is 1.1 millimeters per year, and the ocean mass is 2.1 millimeters per year. I'm going to go and talk a little bit in details of these contributing factors. So the steric height is an indicator for how the change in increasing ocean heat contain changes the sea surface height over time. So basically is a measure for how the ocean is expanding due to an increase in heat content. You will know this commonly as thermal expansion. As you can see from this time series, it's been steadily increasing the last 20 years or so. How do we measure this? We have gridded temperature and salinity of the oceans up to 2,000 meters with Argo floats. Argo floats are autonomous vehicles that change their buoyancy and profile along the water column, allowing us to have these measurements and other measurements too. You see a couple of pictures of deployments of Argo floats, and on the left-hand side, you see the amount of Argo floats that are actively working in January of this year. This is telling you there's thousands of profiles that allow us to have this specific information. Ocean mass. So ocean mass, and as you can see in this time series, has increased 2.1 millimeters per year. The main contributors are Greenland and Antarctica. As you can see from these images from NASA, we see that in Antarctica, there's areas that there's a decrease of mass of about 1 meter, of ice height of 1 meter, and there's and there's other areas that there's an increase of this ice height. On the other hand, in Greenland, Greenland coastal areas are basically losing mass constantly. Here we have a time series of Antarctica mass loss and Greenland's mass loss. You can see we have 149 gigatons for Antarctica and 279 gigatons per year for Greenland. And 1 millimeter of sea level equals approximately of 360 gigatons, of ice loss. What are the global mean sea level rise projections? So it's likely that sea level is going to rise between 20 to 30 centimeters by 2050. And depending on the global warming scenario, there's going to be an increase of 50 to 7 centimeters for the RCP 4.5 scenario, and the RCP 8.5, there's 40 to 100 meters. Basically, depending on the global warming scenarios that we follow, the measures that we're going to take, we're going to have the level of sea level rise, sea level change. In the most extreme scenarios, you can see here on orange and red, we have up to almost 2.5 meters of sea level rise. So now we're going to look into what the state of the world beaches. Through satellite data, scientists have been able to measure the changes in coastal environments, especially on sandy beaches. From this map, you can see that the changes are not homogeneous around the world, and the changes depend on different reasons. One of the main reasons is sea level rise. 24% of the world's sandy beaches are eroding at rates of 0.5 meter per year. This is a global average. There are some areas that the increase is even higher. And 28% are accreting, meaning gaining sand, and 48% are stable. The majority of the sandy shorelines in marine protected areas are eroding, so this is a high concern for coastal conservation. So now I'm going to talk about Save the Waves Coalitions. Save the Wave Coalitions is an NGO that protects, stewards, and defends surf ecosystems around the globe in coalition with diverse organizations. So its mission is to protect and preserve coastal environments with a focus of surf zones. They achieve these goals through protected areas, economical studies, and direct actions in partnership with local communities. So now I'm going to explain you what a surf ecosystem. A surf ecosystem is the coastal environment around a surf break. It has different components. You have the geophysical component, which are the physical attributes, bathymetry, sediment transport, the swell window that allow to have a surfable break. There's the biological component, which are the flora and the fauna, and the socioeconomic components, which is the history of the coastal environment, the human history of the coastal environment, the economic activities around it, and these are not necessarily related to surf specifically. The culture around the surf ecosystem, there's increasing surf culture, but there's also they're strongly related with fishing culture. This is one of the places that I'm working with Save the Wave to protect is in Punta Conejo in Oaxaca. That has unique characteristics of a surf ecosystem that we're working really hard to protect against the construction of an industrial port. So how is sea level related to a surfable wave or a surf ecosystem? Sea level rise. On top we have a scenario in which a surfable wave only breaks in a mid-tide condition. There's a specific conditions, geophysical conditions that allow us a surfable wave. And there's been a study by Raymond et al. Where they use local knowledge to look into the danger of the threat of coastal surf ecosystems in California. So basically, there's three scenarios from this study. A natural adaptation in which there's a landward migration of the surf spot with a landward migration of the sandy beach due to sea level rise. So basically, the surf spot moves with sea level rise. It will be the same? We don't know. There's another scenario where natural adaptation is inhibited, in which this landward migration of a surf spot is inhibited by a seawall. Seawalls are the major protections against sea level rise for infrastructures, coastal infrastructures. They're not always works, but that's what it's naturally built. So in this case, the surf ecosystem disappears. And there's this natural adaptation that's impossible due to a cliff that doesn't allow that landward migration of the surf spot. This is a natural adaptation due to sea level rise. So how do we use sea level rise information in Save the Waves? So for Save the Waves, together with the University of Baja California, we've developed a multi-criteria analysis to identify priority areas for surf ecosystem conservation. We proposed a set of indicators to measure the state and pressures on diverse surf ecosystems using GIS systems in Mexico. and we're transferring this methodology all around the world. So how are we going to use sea level rise information? Currently, we're working on including in this multi-criteria analysis sea level rise projections to account for the effects and in surf ecosystems and analyze the threat that sea level rise will have on surf ecosystems. For everyone working in coastal conservation, climate change and sea level rise have become a major concern, and we're working towards mitigating its effects with different strategies. You can see more information in the Save the Wave webpage and in some of our partners like the Surfrider Foundation and Wild Coast. Thank you very much.
Thank you very much, Dr. Pasalacqua. We just heard about sea level rise, and next we'll be moving on to discussing sea ice loss with Dr. Till Wagner. Dr. Wagner is an assistant professor in the Department of Physics and Physical Oceanography at the University of North Carolina, Wilmington. His research focuses on how ice in the polar region grows, moves, and melts. He is also working to understand how changes in the polar regions are connected to the changing climate. To do this, he uses a combination of mathematics, computer models, satellite observations, and measurements collected directly in the polar regions. Dr. Wagner completed his PhD in applied mathematics at the University of Cambridge and spent his postdoc years at Scripps Institution of Oceanography. Thank you very much, Till.
Welcome. My name is Till Wagner. I'm an assistant professor in physical oceanography at the University of North Carolina, Wilmington. And it is my great pleasure to talk to you today about the rapid observed sea ice loss in the Arctic over the last half century or so. Before I start looking at sea ice in detail, I wanted to provide some background about the difference between land ice versus sea ice. So on the left here, we have a map of the southern hemisphere with Antarctica at the center. And on the right, we have a map of the Arctic Basin, located at the center of the northern hemisphere. So in the modern day climate, there are two major land ice sheets. An ice sheet is a large body of land ice, and we have the Antarctic ice sheet on the left and the Greenland ice sheet on the right. Now, land ice is formed by falling snow that compresses over hundreds of thousands of years and turns into ice and creates these large bodies of ice. And they can be up to 4 kilometers thick in the modern day climates. Now, the Antarctic continent is surrounded by the Southern Ocean. And in the winter, that ocean freezes over and gets covered by a thin layer of sea ice. So sea ice is just the frozen top of the ocean, and it is much thinner than the land ice. It's typically 1 to 2 meters thick, if that. The same is occurring in the Arctic. The Arctic basin is covered partially all year round in sea ice, and in the winter, the sea ice extends to the peripheral seas as well. So the main point of this slide for me here is that land ice, which sits on land, when that melts, it contributes to sea level rise because you're adding a new volume of water to the existing ocean. Whereas sea ice, on the other hand, is already floating in the ocean. And when sea ice melts, you're not adding any new mass to the ocean. And so sea ice is actually not contributing to sea level rise. So why do we care about sea ice? Well, I'll get back to that in a minute. But first, I wanted to give a little bit more detail on the Arctic sea ice seasonal cycle. So here I have a visualization from the NASA Scientific Visualization Studio. And what we are looking at here is the Arctic sea ice cover as it grows in the winter to extend to low latitudes and then melts back every summer. So in the winter, it grows to up to 16 million square kilometers. and then it shrinks back every summer to something between 6 and 4 million square kilometers. If we plot the area as a function of the day of the year, that's what I've done here, you will see the seasonal cycle. Every curve here corresponds to 1 year. And we've been doing this since the beginning of the satellite era in 1979. So every year we have a maximum sea ice extent at the end of winter in March, and then at the end of summer in mid-September we have a minimum. If I color these curves by the year taken, then you will see a very interesting pattern. The bright beige here is the early years, the earliest being 1979, and the latest one here is 2019. And you can see that over the years, sea ice has become less and less. And this is most pronounced in the September minimum. So I wanted to focus here on the evolution of the September minimum. If we're looking at all these measurements and plot them, the area as a function of the year, you're finding this steady decrease. There's some natural variability between years, which is kind of like the differences in cold winters that we experience and warm winters. But overall, you see that we have started in 1979 with close to 8 million square kilometers of sea ice area in September. And nowadays, we have something closer to 4 million square kilometers. So in 79, the ice cover looked roughly like this in September. And in the summer of 2019, there was only about 60% of this left. So over the last 40 years, we have every decade, lost about 10% of the original ice cover. Now, you might wonder, how accurate are these measurements? And how do we even know all of this? And the broader question is actually, how do we carry out Arctic science? And so that's what I wanted to talk about next. These data that I've just shown you are all collected using satellites. Satellites have become extremely sophisticated and are very good at measuring the areal extent of sea ice. So the data that I've just shown you, we know with a high degree of certainty. Satellites are not as good at measuring the thickness of sea ice. So if we try, for example, to compute the volume of sea ice, our estimates have a much higher uncertainty than for just the area. And also satellites are limited. They don't tell us much about the ocean underneath the ice. They don't tell us really much about the conditions of the ice itself. So we also have a second pillar of Arctic research, which is field observations. We go to the Arctic to take measurements of the ice itself, of the ocean underneath the ice. Here I'm in Fram Strait with some students. We're extracting ice cores to look at salinity of the ice, at ice age, and also at the biology in the ice and underneath the ice. Satellite measurements and field observations are really good for us to study the past and the present of the sea ice. But we also are interested in what the future is going to look like. And for that, scientists develop ice and climate models. These are typically computer simulations that are fed with current data and obey the laws of physics and project out what the sea ice is going to look like over the coming decades, centuries, etc. Now, why do we care? Since I just told you that sea ice is not actually that important for sea level rise, but it nevertheless plays a hugely important role in the climate system. So, first of all, sea ice is very reflective. It is white and it reflects a lot of the incoming solar radiation. You can imagine if you remove the sea ice from the Arctic Ocean and replaced it with open water, it's a little bit like taking a white t-shirt off and putting a black t-shirt on. You're going to absorb a lot more of the incoming heat. And that has far-reaching implications for the local and for the global climate. Sea ice also, when it grows, produces dense water. And that dense water sinks to the bottom of the ocean and helps drive the global ocean circulation. And then one more thing, it obviously keeps the Arctic air temperatures cold as well. So that in itself has important implications for atmospheric dynamics. Beyond the climate system, the Arctic is increasingly receiving attention from humans. And that is because if you remove the sea ice, you are suddenly left with a new open ocean. So here I'm showing a map that was printed in the New York Times a few years ago that shows potential shipping routes between 2015 and 2030 from Europe and North America to Asia. The green routes that you see here are shipping routes where cargo ships could be traveling without the accompaniment of icebreakers. The red shipping routes would still need icebreakers. But up to very recently, it was kind of unthinkable that you would take cargo through the Arctic. But obviously that would be extremely interesting if you didn't have to go the southern routes anymore. Beyond shipping and transport, tourism is exploding in the Arctic basin. And obviously there is a lot of interest in exploring oil and natural gas extraction in the area, which comes with its own set of promises and risks. And related to that, and in general, very important is the impact of sea ice on the Arctic ecosystem. So, as we all know, the Arctic ecosystem, especially the charismatic megafauna, polar bears and walruses, depend on the sea ice as their natural habitat, as their hunting grounds. But beyond that, the sea ice is also really important, for example, for spring blooms of algae, where the meltwater helps drive these blooms. And the formation of dense bottom water also drives upwelling, which provides nutrient-rich waters from underneath, which in turn also is a crucial component for the Arctic ecosystem. So the sea ice is important, to sum up, for the physics of the climate system, for human interests, and for the local ecosystem. So to finish up with, what can you do about it? What can we all do about sea ice loss and the challenges it presents for the global oceans? And this is always a tricky question because the Arctic is somewhat of an abstract concept, and the dynamics and sea ice is a phenomenon that are occurring in a very remote place. And so for me, I've always found that learning and teaching about the polar regions and their importance for the global oceans is one of the best ways that we can help raise awareness and protect. So I've chosen to show a picture here of a workshop that I led with middle school girls as part of the Better Education for Women in Science and Engineering program. And I can just encourage all of you to try and learn and teach our next generation of scientists and citizens to appreciate the importance of sea ice in the Arctic and its importance for the global climate system. Thank you very much.
Thank you very much, Dr. Wagner, for that fascinating talk on sea ice loss. For our next session, we will be exploring coral reef loss with Jen McWhorter. Jen McWhorter's PhD between Universities of Queensland and Exeter explores a unique methodology for improving climate projections on coral reef environments. She began her PhD following 8 years of experience in marine spatial planning, ocean observations, and marine policy, most recently from Scripps Institution of Oceanography at the University of California, San Diego. Commonly seen in the literature, downscaling general circulation models over coral reef environments tend to lack important coastal complexities for climate projections. Ms. McWhorter has been developing a unique method for using vertical 1D physical biogeochemical models to drive various 21st century climate change projections over the Great Barrier Reef. By calculating many 1D individual profiles, The model accounts for key drivers of vertical mixing using local bathymetry, tides, and atmospheric inputs, then outputting various column properties such as surface and bottom temperature and photosynthetically active radiation, or PAR. These projections provide a more detailed analysis of frequency and severity of warming events in the future while using relatively simple computing. As a side note, Jen McWhorter was also my TA, the very first GIS class I took in grad school. So thank you very much, Ms. McWhorter, for coming here. And if any of these maps were done poorly, you can blame her, since she taught me everything I know. Thank you very much, Jen.
So thank you for the opportunity to be part of your AGS conference. I'm Jen McWhorter, and I'm currently working on my PhD at the University of Exeter and the University of Queensland under the supervision of Dr. Paul Halloran and Professor Peter Mumby. The focus of my work is on improving the way we model climate projections globally over coral reef environments. And more specifically, I'm focusing on the Great Barrier Reef as a case study. Oddly enough, I first became inspired to study the ocean when visiting the reef in Australia at age 10, and I learned how threatened the reef was to climate change. As you're aware, sea surface temperatures are warming as an effect of global climate change. Corals live near their thermal tolerance, meaning they're extremely sensitive to warming temperatures. Corals can be thought of as part animal and part plant. They have an algal symbiont that lives in their tissue called zooxanthellae, as you can see in the diagram here. This gives them the colors that you see on a healthy reef. When corals become stressed, they expel this algae into the water column and appear white. Their tissue is then transparent, and what you're seeing is their skeleton. At this point, the corals are not dead, and they can actually regain this algal symbiont, but if the warming persists, the stress can lead to mortality. This is what a dead reef looks like, and eventually the structural integrity will break down. On a global scale, 2014 to 2017 was an unprecedented period of successive record hot-breaking years, which coincided with the most severe, widespread, and longest-lasting coral bleaching event ever recorded. During the 2014 to 2017 warming event, the Great Barrier Reef was greatly impacted. For scale, the Great Barrier Reef is the largest tropical reef system in the world, nearly the size of the entire east coast of the United States. These maps were created using aerial surveys by Professor Terry Hughes and team, and these aerial surveys captured the last 3 mass bleaching events. These events were large-scale and resulted in a great loss of coral. The bleaching extended even into portions of the southern Great Barrier Reef in 2020. As you can imagine, reoccurring years of severe bleaching with little time in between provides less of a window for recovery. So now you might be wondering, what can we expect into the future in terms of magnitude and frequency of severe bleaching events? It is important to know that climate models provide useful information of past and future large-scale climate variability, but they have coarse resolutions and they're unable to resolve certain physical complexities over coral reefs. Before I begin diving into my research, I just want to mention that these results have yet to be published. In order to improve climate modeling, we've developed a method to bring in atmospheric inputs from the climate models over the reef and into the water column. Our technique takes into account the bathymetry details, the locations of corals, things like clouds, pressure, humidity, winds, tides, various mixing properties, and then it simulates a vertical one-dimensional heat transport through the water column. We then repeat this simulation over various points on the reef at our specified resolution and within certain depth constraints. The temperatures throughout the water column at each point will have different properties. After running this vertical simulation on the Great Barrier Reef for various climate models, we now have these results. This figure is showing the magnitude or the intensity of warming in terms of coral stress on the y-axis. This is a commonly derived metric that indicates how long a warm anomaly persists over the reef. When this number reaches 8, is typically when we see coral bleaching leading to mortality. The different lines on this plot are referencing different future climate scenarios in terms of long-wave radiation or energy that's being emitted from Earth. These climate scenarios take into account various socioeconomic and physical processes that cause changes to our global temperature. The highest climate scenario is indicated in red at 8.5 watts per meter squared. This is also known as the worst case climate scenario, and this refers to global average temperatures reaching near 5 degrees Celsius by 2100. The scenario assumes an energy-intensive fossil fuel-based economy. The next scenario is the 6.0 watts per meter squared, and this refers to roughly 3 degrees of global average temperature warming by 2100. And this lends a pessimistic development trend described as little investment in education or health, a fast-growing population, and more inequalities. The 2.6 watts per meter squared scenario accounts for a significant shift in sustainable practices. And finally, the lowest scenario is the 1.9 watts per meter squared. And this is the preliminary candidate for staying below the 1.5 degrees C of warming by 2100. It considers a decline to zero emissions, followed by a long period of negative CO2 emissions. These climate scenarios can range in variability, which is why I show a number of outcomes. It is thought that we might be headed somewhere between the orange and the blue lines. As you can see in the figure, the two low scenarios slightly rise from conditions similar to what we've seen today until about 2048, indicated by the gray vertical line. This is when that lowest scenario peaks. Meanwhile, the high scenarios increase rapidly in the intensity of warming. So those two low scenarios remain close to that 8 threshold where we typically experience severe bleaching. Now that I've showed the magnitude of warming projected for the Great Barrier Reef, as I mentioned, it's important to look at the frequency of these events. If there's less time in between warming events, there will be less time for recovery from bleaching. This figure shows the climate scenarios as when they're expected to experience severe bleaching leading to mortality within a decadal window. As you can see, we have a committed warming of 3 to 4 severe bleaching years per decade, even in the best case, lowest scenario of 1.5 degrees C. For context, if you remember earlier, we've just experienced 3 events in the past 5 years on the Great Barrier Reef, which resulted in widespread bleaching and mortality. In contrast from the lowest scenario, the highest scenario is projected to experience severe bleaching events nearly every year by the end of the century, and roughly 7 out of 10 years around mid-century. Coral reefs support fisheries and tourism. They're one of the most biodiverse spots on Earth, and they've been considered the rainforest of the ocean. Coral reefs not only provide food and tourism revenue for coastal communities, they provide protection from storms by creating a physical buffer. Coral reefs also provide an intrinsic value. We simply like knowing that they're there. For the sake of corals, we need to continue on the lowest possible trajectory. As individuals, it may be hard to see how you can make a difference on such global policies, but by making sustainable choices every day, we can all contribute to reducing our impact on the planet. Other things you can do that will really make a big difference are educate and inspire. This is a photo of me when I was 10 years old on the Great Barrier Reef, and the tour operator informing me of the impacts of climate change to corals changed the course of my life. We can also continue to promote equality, such as encouraging young women to pursue science careers. Thank you for your time.
Thank you very much, Jen, for that talk on coral reef loss. For our next topic, we'll be moving to ocean deoxygenation with Dr. Natalia Gallo. Natalia Gallo is a marine ecologist and biological oceanographer currently working as a postdoctoral researcher with the Cal Coffee Long-Term Ecosystem Monitoring Program at the Scripps Institution of Oceanography, UCSD. Her research focuses on climate change impacts on deep sea fish and fishery species. She is also an affiliate of the NOAA Southwest Fisheries Science Center and the Center for Climate Change Impacts and Adaptation at Scripps. She is passionate about the science policy interface, using science to inform ocean-based climate mitigation and adaptation actions, and has participated in multiple UNFCCC international climate conferences. She is a previous Switzer Environmental Leadership Fellow, National Science Foundation Graduate Research Fellow, and honoree on the Forbes 30 Under 30 Science list, and UCSD TEDx presenter. Thank you very much, Dr. Gallo.
Hello, my name is Natalia Gallo, and I'm a postdoctoral researcher at the Scripps Institution of Oceanography. Today, I want to talk to you about why the ocean is losing oxygen and what you can do about it. But first, let's pause and look at this beautiful photograph of a healthy marine ecosystem. Now take a deep inhale. What's happening in your body is that your bloodstream is now carrying new oxygen to all the cells in your body, fueling them and allowing them to perform their essential functions that keep you healthy. But like you, every animal in this photograph is also breathing, though the mechanisms look a bit different from the way in which we breathe. Every fish, coral, and anemone that you see here is extracting a dissolved form of oxygen from the surrounding seawater. And just like us, every animal in this picture has certain oxygen requirements that must be met so that it can be healthy and live in this habitat. Beyond the animals you can see with the naked eye, if we took a drop of seawater and put it under a microscope, we would see millions of microscopic organisms, phytoplankton and bacteria. The vast majority of all of these microscopic organisms also need oxygen to thrive and perform their roles in the ecosystem. As you can see, the ocean is filled with organisms that need oxygen. But what I'm here to talk with you about today is that the ocean is losing oxygen in a process known as ocean deoxygenation. It's a bit of a mouthful, but take a moment to pronounce it with me so that you can feel confident about saying it. Deoxygenation. Ocean deoxygenation. This just means a decline in the oxygen content of oceanic and coastal waters. This decline is primarily driven by eutrophication, which is otherwise known as excessive nutrient inputs into waterways, as well as climate change. In this map, you can see colored in red and blue all areas in the ocean where conditions are already hypoxic. Hypoxic conditions mean that oxygen levels are low enough that they are already stressful to most animals. All of the red sites show coastal hypoxic areas, which have increased rapidly in number and are sometimes referred to as dead zones because they are often associated with mortality events of fish and other hypoxia-sensitive animals. In blue, you can see the regions of the ocean which already have hypoxic conditions at certain depths of the water column. These regions are called oxygen minimum zones and are expanding due to climate change. Ocean deoxygenation can be thought of as an oxygen supply and demand mismatch. Eutrophication and warming from climate change are decreasing the supply of oxygen while increasing the demand for oxygen in the marine environment. On the next slide, we'll talk a little bit more about the actual mechanisms. The ocean is a critical heat sink and has absorbed approximately 93% of the excess heat in our climate system from the burning of fossil fuels. When the ocean warms, however, the oxygen content of the ocean also decreases. This is due to a few factors. First, solubility. Warmer water holds less oxygen, so as ocean temperatures warm around the world, the ocean loses its ability to hold as much oxygen. You can think of this kind of like outgassing of a hot soda. Oxygen also enters the ocean from the air through mixing at the surface of the ocean. As surface waters become warmer with climate change, they become more stratified, thus reducing how much oxygen is actually getting mixed into the water. Ocean warming also leads to changes in the circulation of the ocean. As the ocean becomes more sluggish, deeper waters are supplied with less oxygen. Meanwhile, as temperatures warm, oxygen demand by marine organisms and bacteria increases. In coastal areas, these warming-driven changes in oxygen are further exacerbated by excess nutrients that enter waterways, causing algal blooms that lead to low oxygen events as they decompose. Together, solubility changes, decreased mixing, changes in circulation, increased respiration, and excess nutrients all contribute to the loss of oxygen in the global ocean and coastal zones. Ocean deoxygenation is a topic that has only recently received a lot of attention. When I first started out with my PhD at Scripps, very few people who I spoke with had even heard about ocean deoxygenation. This cartoon from Baz Kohler captures well my experience speaking about ocean deoxygenation to the public and to policymakers. Here, the fish are fleeing due to deoxygenation, but the customs official says he has never heard of that nation. The last few years have seen a huge expansion in the research on ocean deoxygenation, as well as compilations of knowledge from scientists. Just last year, the International Union for Conservation of Nature published a giant report bringing together the state of the science on ocean deoxygenation. Ocean deoxygenation is now a very active area of research, and scientists all around the world are working to understand how much oxygen loss has already occurred, what the ecosystem impacts of oxygen loss are, how much oxygen loss is projected for the future under different climate scenarios, and how oxygen loss interacts with other ocean stressors that you've been hearing about today. Briefly, what we already know is that ocean oxygen loss is a substantial problem. Using long-term measurements of ocean oxygen taken from all around the world, scientists have found that since approximately 1950, the ocean has lost about 2% of its oxygen. In the figure on the left, in red, you can see all of the areas where oxygen loss has occurred, and areas in darker red have experienced larger losses than the global mean. Climate models project more rapid oxygen loss in this century, and by 2100, global oxygen levels are expected to decrease on average by 3 to 4%. In the figure on the right, you can see climate model projections for oxygen loss for the most recent climate model comparison. Oxygen declines throughout the 21st century, but less oxygen loss occurs under the most ambitious climate policy scenarios, which you can see here in the purple and the blue lines, compared to the business as usual scenario, which you can see with the red line. While 3 to 4% decrease may not seem so large, small changes in oxygen matter, and certain regions experience much greater oxygen losses. In coastal areas, these climate-driven losses of oxygen are further exacerbated by increased microbial demand for oxygen due to the influx of increased nutrients and organic matter. Since nearly every organism in the ocean needs oxygen, oxygen plays a key role in structuring marine ecosystems and affects where species can live. For example, species that are very active and have high metabolic requirements, such as tuna, can only live in well-oxygenated habitats. Other species, such as this marine worm here, have evolved special adaptations that allow them to live in hypoxic environments. For this reason, hypoxic areas are not dead zones, because certain hypoxia-tolerant species can thrive in these areas. However, mortality events of hypoxia-sensitive species, such as the crabs and the fish pictured here, often occur when coastal regions experience hypoxia. The ecosystem and societal implications of ocean deoxygenation are changes in species distributions, food web changes, decreased biodiversity, impacts to fisheries, and also potential climate feedbacks. Nitrous oxide, which is a potent greenhouse gas, is actually produced in low oxygen regions of the ocean when microbes use nitrate and nitrite instead of oxygen to breathe. As I mentioned before, the field of research around ocean deoxygenation is rapidly growing. My own research has examined how oxygen structures deep-sea fish communities and explored some hypoxic superstars, animals such as this cusk eel and cat shark that are LIGO-oxyphiles, or low oxygen specialists, and can thrive under oxygen conditions that are lethal to most fish. I have also used new tools such as deep-sea landers and worked with long-term data sets like the Calcoffee Ecosystem Monitoring Program to study species vulnerability to oxygen loss across both short and long time scales. This research contributes to understanding of the ecosystem and fisheries impacts of oxygen loss and how we can best manage these changes. I hope that you've enjoyed this presentation, but I also hope that you are listening with the intent not just to learn, but also a drive to do something. So here are a few things you can do. First, be informed and share your knowledge about ocean deoxygenation. There are a few excellent new resources, such as from the UNESCO GONE Group and the IUCN Ocean Deoxygenation Report, that I highly recommend. Second, look for personal changes you can make to decrease your own contributions to ocean deoxygenation. These include transitioning away from fertilizer-hungry lawns, calculating and lowering your carbon footprint, and making purchasing choices that support more sustainable food production practices. But personal choices only get us so far. Sound and ambitious climate and watershed management policies are necessary to prevent and manage further ocean deoxygenation. Be active and demand ambitious policies from your representatives at the local, state, national, and international levels. Thank you for your interest and your attention, and I hope you feel empowered to make a difference.
Thank you very much for that discussion on ocean deoxygenation, Dr. Gallo. Next, we'll be hearing from Dr. Matthew Costa, who will be discussing mangrove deforestation. Dr. Costa is a postdoctoral scholar in the Center for Climate Change, Impacts, and Adaptation at Scripps Institution of Oceanography. He completed his doctoral research at Scripps on sediment carbon stocks in mangrove forests across northern neotropics, conducting sampling across Panama, the Galapagos Archipelago, and Mexico. He completed his postdoctoral dissertation, Mangroves in Depth, Long-Term Carbon Burial Across Spatial Scales, in 2019. Prior to study at Scripps, Dr. Costa researched coral reef and mangrove ecology at the Bermuda Institution of Oceanography, or of Ocean Sciences, as an undergraduate in ecology and evolutionary biology at Princeton University, completing a bachelor's thesis on mangrove species donation in 2011. Dr. Costa's current work focuses on coastal blue carbon and flows among coastal ecosystems in La Jolla and sequestration of carbon in protected and restored wetlands in San Diego. Thank you very much, Dr. Costa.
Hello, my name is Matthew Costa. I'm a postdoctoral scholar at the Center for Climate Change Impacts and Adaptation at Scripps Institution of Oceanography, University of California, San Diego. And today I'll be talking to you about the global issue of mangrove deforestation. So what this globe represents is the global distribution in purple or pink on the subtropical and tropical coasts around the world. So first I'll discuss what are mangroves, and then we'll talk about what is their global status around the world. So mangrove is a swamp. That is a type of wetland that's dominated by trees, and specifically a type of swamp that lives in salty environments, so the marine coastal environment. The different mangrove species are found in different, what we call intertidal zones, so different locations in the intertidal zone. The red mangroves, as you can see here, with their prop roots, help them live in the low intertidal, closer to the ocean, whereas other species live higher up in the intertidal zone, such as the black mangrove, whose above-ground root structure is called pneumatophores. You can see here, these are found higher up in the intertidal zone. Not just the trees have this sort of intertidal zonation, but the creatures that live on all of these roots show this zonation as well. So the roots of mangroves create a habitat for an amazing and beautiful diversity of encrusting invertebrates, algae, and microorganisms. And these organisms also are zoned in the intertidal on their root habitats, which is really amazing. So even though there are only a few different mangrove species of trees in any given location, the abundance and diversity of other organisms is incredibly high. So we have encrusting invertebrates and algae on the roots, scavenging and predatory crabs, also predators from the air, such as birds from land and ocean, as well as a diversity of juvenile fish and other marine organisms that use the mangroves as nursery habitats. All of these different kinds of diversity, as well as many, many microorganisms you're just beginning to understand, are housed in the mangrove ecosystem. Unfortunately, these incredible and diverse ecosystems are being lost rapidly around the world. This time lapse shows over 30 years the replacement of mangrove and coastal forest ecosystems in Quintana Roo, Mexico. So what do we know about this loss of mangrove ecosystems around the world? It's been estimated that by the end of the 20th century, more than 35% of mangrove area was lost globally. Some of these, during the late 20th century, these rates of mangrove loss were observed to be highest in the Americas, actually reaching rates of up to 2% of global mangrove area lost per year. And where one of the major risks, and especially in the Americas, in some places, were the conversion to shrimp pond aquaculture, as you can see in this picture. Today, it's estimated that about 137,000 square kilometers of mangrove remains around the world. And in the last 20 years, since 2000, the shifts in global deforestation trends there's been a shift that's occurred toward Southeast Asia. So if you look at this graph, where Southeast Asia has the most red, not only in total mangrove loss in hectares, and that's partly because there's just so much mangrove area in Southeast Asia, but also mangrove loss as a percentage of original area. As you can see here, in both cases, you have a lot of red in this part of the world, showing highest rates of mangrove loss in Southeast Asia. This graph gives you a better idea of what are the drivers locally and regionally in mangrove loss in different parts of the world since 2000, where we have, there's a lot of information here. So these squiggly lines at the top and at the side represent the longitudinal and latitudinal distribution of mangrove deforestation around the world. What I'd really like you to focus on is these colored squares on the map. So the colored squares represent sort of mangrove cover around the world, and the color of the squares represent the major cause, the major driver of mangrove deforestation in that region, where red squares represent replacement of mangroves for settlement, orange represents the replacement due to production of commodities, such as for agriculture or aquaculture, so fish farms, shrimp ponds, etc. Non-productive conversion represents the loss, and that's yellow, represents the loss of mangroves unintentionally due to land use changes perhaps somewhere else, as we'll discuss later. Green represents extreme weather events, such as major storms, and blue represents the loss of mangroves due to erosion. And these sort of big squares at the bottom summarize what the major drivers of mangrove loss are in different regions of the world. So C and D, these are North and South America. Here and in Oceania, you have dominating are the causes of extreme weather events and erosion. Whereas in Africa, non-productive conversion plays a bigger role. And in Southeast Asia, which again is the hotspot of mangrove area overall and also of mangrove loss, is dominated by conversion to commodities, especially today, palm oil plantations. So it's easy to imagine how conversion to a plantation or settlements could damage wetlands, such as mangroves, but also it's possible for, in the case of the yellow non-productive conversion, decisions that happen many miles away can really negatively impact mangroves on the coast. And a clear example of that is this study by some of my colleagues, Excura et al. In Mexico, where they showed that we have 4 rivers here that go into the Pacific Ocean. These top and the bottom ones have hydroelectric dams many miles upstream, which as an unintended consequence prevent a lot of sediment from reaching the coast. And as we see in this column here is showing in red, the area that is lost mangroves from the delta on the coast over several years, whereas in these dammed rivers, whereas the undammed rivers have stable coastlines. So this is an example of how these sort of non-productive conversion of mangroves can be a really big problem in coastal areas. In addition, even the loss of mangroves due to extreme weather events and erosion are related to human activities, because extreme weather events are increasing in intensity due to climate change. And this is an area of mangrove dieback in Baja California, where wave and weather events have killed the fringe or the edge of the mangrove environment, and so they've died back. So these extreme weather events are increasing due to climate change, and also sea level rise is accelerating due to climate change, and as a result, mangroves that are experiencing erosion are further challenged by rising sea levels. So, why, you might be asking yourself, why should I care about these mangroves and maybe in places in part of the world that I don't even live in? Well, I think that these ecosystems are valuable in their own right, but if you need more convincing than that, there's actually something in it for us. Mangroves produce lots of what we call ecosystem services. So these are processes that are carried on by ecosystems that provide economic value to humans, and they do it for free. Mangroves support fisheries species, so species that we catch and sell and eat. They improve water quality. They foster lots of other valuable biodiversity. They counteract erosion by depositing sediment, and they protect coastal areas from the impacts of storms, saving lives and property. And they sequester carbon, which is my special area focus on my research. So really interesting that mangroves are both threatened by climate change, but they're also one of our best allies in fighting climate change, as we'll discuss. So here, very quickly, I'll show you some carbon sequestration data in different ecosystems where we have a logarithmic scale on the y-axis, so that's really important to notice, of carbon burial and grams of carbon per unit area per year. And what this shows is that these ecosystems, what we call blue carbon ecosystems of salt marshes, mangroves, and seagrass beds, sequester about 100 times more carbon, or sequester carbon 100 times faster than these terrestrial forests. And that's because these ecosystems have sediments that are accumulating and that really help bury the organic matter and preserve it in the ground maybe for thousands of years. So these are really effective carbon sinks. So in light of climate change, destroying these ecosystems is really the last thing we should be doing, and yet that's what's happening around the world. So the good news is that it seems that mangrove deforestation rates have been slowing down in recent years, and so if you want to contribute to positive movement in this direction, what can you do about it? Locally, you can support restoring coastal ecosystems, either volunteering, getting out there yourself, restoring ecosystems, and promoting their use as sort of the green infrastructure that they are for coastal adaptation and resilience. And even if you don't live near mangroves, as I do, you can get into your local coastal ecosystem or other ecosystem, such as, for me, that's the salt marshes in Mission Bay, to help protect them and support their ecosystem services. So even if you live someplace without mangroves, you have something you can contribute to. Globally, there are lots of things you could do to reduce your ocean impact on ocean ecosystems, including reducing your carbon footprint, which again, climate change is impacting these ecosystems around the world. Reducing your plastic pollution can help make sites like this of really plastic impacted growth forests less common. And you can be an informed consumer, being careful not to consume goods that were made by destroying mangroves or other forests. But I'd like to end on a positive note. So look at this graph, which shows the top 15 countries ranked by their mangrove area around the world. And one hopeful piece of information from this is that 50% of the world's mangrove area, so if you see it goes down to here, is in just 6 countries. And 75% of global mangrove area is contained in just 15 countries. So what that means is that if just a few countries set really ambitious goals for protecting coastal environments and using them for climate change mitigation, the global mangrove deforestation problem would be essentially solved. And so what this requires is international support and pressure. And we have there's a process for this, which is through the United Nations, called the Paris Climate Agreement. And that's why it's so important that the president-elect has announced that the United States will rejoin the Paris Climate Agreement. And we have to keep calling on our elected officials to, regain American leadership in this sort of international push to fight climate change, including by protecting these ecosystems, which can be our best natural allies in fighting climate change. So with that, I'd just like to say thank you for listening.
Thank you very much, Dr. Costa. Mangrove deforestation has always been one of my favorite subjects in this session because I knew so little about it. Thank you very much for illuminating that topic for all of us today. Next, we'll be hearing about a topic that is near and dear to my heart as well, ocean plastics, with Dr. Jennifer Brandon. Dr. Brandon received her PhD in biological oceanography at Scripps Institution of Oceanography in 2017, focusing on nascent field and marine microplastics. She is an expert in quantifying and identifying marine microplastics and has developed multiple novel methods to identify the smallest sizes of microplastics and determine the age of plastics exposed to varying weather conditions in the environment. She was the first to find temporal trends of microplastics in the sediment record, and the exponential increase of microplastics she recorded from 1945 to 2009 closely correlates with exponential increase in worldwide plastic production over the same time period. She also has an extensive knowledge in marine ecology, having spent much of her PhD doing lab and field work on the California current ecosystem, plankton ecology, and how microplastics affect the bottom of our food web in that region. Dr. Brandon is highly accomplished in the world of scientific communication, having given hundreds of interviews and lectures to all types of stakeholders, and recently completed her tenure as a Price postdoctoral fellow in science communications at the Birch Aquarium at Scripps Institution of Oceanography, where among her other duties, she taught graduate and undergraduate courses in communicating science to the public. She has been interviewed by BBC, NPR, The Guardian, and the Los Angeles Times, among many other organizations. Thank you very much, Dr. Brandon, for joining us today.
Hi, my name is Dr. Jennifer Brandon. I'm a biological oceanographer who studies plastic pollution in the ocean. As you can see from this globe, ocean plastics are a worldwide problem. We find them around the ocean, but especially concentrated in the 5 subtropical gyres. So in this diagram, you'll see the pink areas that are concentrated in the middle of the ocean. Those are the subtropical gyres where the plastic concentration is the most dense on the surface ocean. I'm going to talk a little bit about how the plastic gets there and why it's so concentrated there. So ocean pollution is a relatively new problem. Plastic is only about 100 years old as a substance. It was invented in 1907, but we didn't widely use it until World War II and right after World War II. But since then, we have had an exponential growth in global plastic production, and we are currently up to approximately 407 million tons of plastic produced annually worldwide. And of that 407 million tons, approximately 4.8 to 12.7 million metric tons enter the ocean annually. That plastic gets into the ocean from polluted rivers and harbors, like these 2 bottom pictures show you. Those rivers flow into the ocean. Dirty harbors drop it into the ocean off of ships, and that flows through currents into the subtropical gyres, where it gets stuck, sometimes indefinitely. And there is an estimated standing stock of 5.25 trillion pieces of plastic floating on the ocean's surface. But that's just what's floating on the surface of the ocean. What's sunk to the bottom of the ocean is actually vastly understudied. And so we are really just kind of at the beginning of studying how much plastic is currently in the ocean. What you think of when you think of plastic in the ocean is often those last pictures of really polluted rivers, large pieces of plastic, or this top image on the right of a really big thing of nets, large tires floating in the ocean, animals entangled in plastic. But that's actually not what most of the plastic in the ocean looks like. Over 90% of the plastic in the ocean is microplastic, or plastic that's smaller than 5 millimeters. So in our lab at Scripps Institution of Oceanography, we counted over 32,000 pieces of plastic from the Pacific subtropical gyre, and we found that over 90% of them were smaller than 5 millimeters. To give you a reference of how big 5 millimeters is, that's half the size of an M&M. So this is really, really small plastic. I then went and looked at even smaller plastic than that had kind of been missed in earlier studies, and I found that we were actually underestimating how much plastic is in the ocean by an order of magnitude of 5 to 7 orders of magnitude of plastic. So the plastic in the ocean is tiny. It's the vast majority of it by number is tiny, little minuscule microscopic pieces. These pieces can be fragments that are from larger things that have broken down. They can be from fibers that are coming off of ropes. They're coming off of our clothing, and they're getting into the ocean. They can be from microbeads that are manufactured to be that small, or they can be from nurdles, which are pre-production pellets that are made to be that small. The reason that microplastics are the issue in the ocean when it comes to plastic pollution is that they can enter every layer of the food web. They can be eaten by really tiny things like plankton, which are the base of the oceanic food web, all the way up to something like a blue whale that filters vast amounts of water and are eating microplastics as well. And microplastics have the potential to bioaccumulate in tissue. So they're small enough that they can actually enter into the muscle tissue of animals and then be eaten and bioaccumulate up that way. We've started to find them in pretty much every environment we look for them in. So we're finding them in sea ice, we're finding them in rivers, we're finding them in oceanic sediment. We've begun to find them traveling around in the atmosphere because they're so small and buoyant. And we've even begun to find them in inland soil. So this is no longer just an oceanic problem. And we are also finding them in human food sources as well. So we depend on the ocean for many things, including seafood, sea salt, and our own drinking water can come from desalination plants. But also fresh water is now contaminated with microplastics. So we're beginning to see microplastics in our daily lives. So the implications of this are manifold. I did a study where we looked at microplastics in oceanic sediment. And this top graph shows that we found sediment plastic deposition at basically the same rate as that graph I showed you on the first slide of world plastic production. So if you see that these two graphs have basically the same slope, that shows that we are leaving plastic in our marine sediment at the same rate as world plastic production, meaning we are leaving plastic behind in what is going to become our fossil record. So as you think about the Bronze Age or the Gold Age or the Iron Age that you learned about back in history class, we have the potential to be known as the plastic age in future history, because that is what we are leaving behind in our fossil record, which I would not say single-use plastic is maybe our greatest invention, but it is what we are leaving behind. Humans are consuming plastic. We now know enough to say definitively that we are consuming plastic. Some studies say that we eat about 5 grams of plastic a week, which is approximately the same size as a credit card. That is a lot of plastic. The health effects of that are unknown, but we do know that plastic has harmful additives and chemicals in it. And we know that we are harming animals with this plastic. So we know that 1 in 3 species of marine mammals have been entangled in marine litter. Every other sea turtle that is out in the ocean, so 52% of sea turtles out in the ocean have consumed marine plastic. 86% of sea turtle species have consumed plastic, as well as many seabird species. So we're harming animals that we care about that are endangered, as well as animals that we depend on for seafood. So what can we do about this problem? The great thing about ocean plastic is that this is a consumer-driven problem and a relatively new problem. We got into this problem in about 50 years, so we can probably turn it around in about the same amount of time. And because it's a consumer-driven problem, there's a lot of consumer-driven solutions. So probably the easiest one that you've probably heard about is bringing reusable cups, bottles, straws, and bags everywhere you go, and refusing things like coffee lids and straws when you have forgotten your reusables. You can also buy in bulk. So when you're at the grocery store, not buying everything plastic lined, but actually buying things in bulk can really reduce your plastic footprint. You can buy non-plastic reusable alternatives to many everyday items. You can participate in beach cleanups, especially if you live on the coast. But if you don't live on the coast, you can clean your local lakes and rivers. And pretty much all of those rivers will eventually end up in an ocean. So that plastic will eventually get out into my samples. So we appreciate it. And you can get involved in banning single-use plastics in your community. So there are a lot of organizations that are involved in the activism side of this, that are working to ban things like single-use styrofoam packaging, banning plastic bags, banning microplastic microbeads in products. So if the activism side of it is kind of more interesting to you, there's a lot of organizations that are doing that on a city-by-city basis. And with that, that is just a brief overview of ocean plastic pollution. And there's much more to say, obviously, but that's kind of the beginning of the talk.
Thank you very much, Dr. Brandon. I especially appreciated your insights into what the average person can do about ocean plastics. Ocean plastics has always struck me as a particularly upsetting problem because it does seem so preventable. So thank you very much for illuminating that for all of us. The next topic we'll be exploring today is one that is equally interesting to me and also equally preventable. It's ocean ambient noise pollution, and we'll be hearing about this from Dr. Kevin Heaney. Dr. Heaney has spent his scientific career exploring the interaction of the ocean environment and acoustic propagation. Some interesting questions addressed include three-dimensional propagation of low-frequency sound across ocean basin and its diffracting behind islands and seamounts, modeling the impacts of ocean waves on multi-static anti-submarine warfare, calculating how far away we can hear fin whales, and parameterizing the ocean soundscape in the presence of anthropogenic noise. After receiving his PhD in Applied Ocean Sciences from Scripps Institution of Oceanography, Dr. Heaney has worked for a variety of companies, from SAIC and Lockheed to more recently Oasis, and had the opportunity to be mentored by many of the great minds from the previous generation, including Dr. Cooperman, Dr. Cox, Dr. Bagro, and Dr. Monk. He has the most fun when he's doing solid science and is able to package that into a system that people, like sailors and managers, find useful. Starting his company, Applied Ocean Sciences, in January of 2019 is a major step forward in combining his passions for solving challenging science problems and getting these solutions into the hands of people who will use them to do good things. On a side note, Dr. Heaney is also my boss, so be nice. Thank you very much, Kevin, for joining us today.
Thank you, Chris, for that introduction. I'm Dr. Kevin Heaney from Applied Ocean Sciences, here to talk about ocean noise and underwater ocean acoustics. I'm super excited to be at a Geography 2050. It's my first foray into this community. But one of the things I like the best about ocean acoustics is how global it is and all of the geography that I get to play with. So I'll be talking about the global ocean challenges. The one in particular I'll be addressing is ocean noise. And so here's a, we have to start with a globe if we're doing geography. This is a global shipping model, which I'll show you later. In real detail, but it just shows you the average sound level for the month of April, over the ocean. This is only shipping; it doesn't include wind. So if you look in the southern ocean here, we're in the South Pacific. You can see that it's very quiet. That's a region dominated by wind. But you can see shipping lanes. You can see in the polar regions, it's noisy, it's shallow. Other places. So the outline of the talk, I'll be talking about sound sources in the ocean, sound propagation in the ocean, marine mammal presence and sensitivity. And I'll be going through global ocean model that we have, look at COVID-19 impacts. We'll talk about the Arctic. These are, so certainly places where there's rising concern about the impact of man-made noise. So first, a bit of background. Sound travels very well in the sea, which is why marine mammals have evolved with the capabilities of listening and sending sound. Here's a plot showing levels and frequency on the x-axis. So very low frequencies are on the left with 10 and 100 hertz. That's what we hear. Up into the 1,000 hertz and 10,000 hertz. This is where the dolphins transmit sound. These blue lines are wind noise for high wind speeds. And you can see they peak around 500 hertz. And the red and orange here are shipping noise in the lower frequencies. And then very loud things are earthquakes, which are louder than everything else, but they're very low frequency. I recommend the docits.org website it's this discovery of sound in the sea for really great background information on all of this stuff. So sound in the ocean doesn't travel straight. It goes up and down depending on the temperature profile and pressure. You can see on the left, if there's a surface ship, sound goes down right away and then it bounces off the bottom and you end up with these refracted paths in deep water. If you're in northern latitudes, the sound speed has a minimum near the surface, and you end up with the sound being trapped near the surface, and sound travels significantly better. You'll see evidence of that in our global sound maps. In shallow water, there's no refraction. Sound just hits the surface and the bottom, and it dies out with range. This is a plot in the Barents Sea. So depending on where you are geographically, the sound can travel in very different ways, and that'll affect the average sound. We anticipate, in the low frequencies, sound will travel all the way across the ocean. So animals and ships are hearing each other from quite a significant distance. So the sound sources in the ocean, the natural sound sources are wind and waves. We think of them together. The wind blows and the waves form, and then the waves break and bubbles make noise. It's a combination of all of the above, depending on your frequency. Rain makes noise, And marine mammals make a significant amount of noise, or an observable amount of noise, and then lightning is super loud. I didn't add earthquakes and volcanoes. They're also in there as well. Anthropogenic or man-made sound sources are shipping, seismic exploration where they're setting off shots, or impulsive sounds to study the seafloor and below it looking for oil. Those can be heard all the way across the ocean basin. Navy sonars of multiple types. Pile driving in shallow water is important. And then explosions. There's lots of unexploded ordnance in the world, and if it's detonated, it makes a significant sound that can be heard a long ways. In particular, the North Sea between the UK and Europe, there's a significant problem of unexploded ordnances, and it affects the ocean soundscape there. So marine mammals and sound. So, marine mammals, and not just mammals, but fish and invertebrates, they use sound for hunting, for communicating, and for navigating. How much so, we're not quite sure, but they do hear each other and talk to each other. And we have recordings of them grunting and using sound while fishing, in particular dolphins. There's a study, this is getting towards the health of the animals in the ocean soundscape. On September 11th, the shipping numbers in the world dropped because of an immediate freeze of the terrorist attacks on global security. But there's a paper put out in the Bay of Fundy, which is eastern Canada. It went from 12 ships in the small bay, which is a loud area, down to 3 ships, and it reduced the shipping noise level by 7 decibels. So that's a number to keep in mind. That's a large number. 3 dB or 3 decibels is twice the amount of energy. And so dropping it by 7 is significant. It turns out to be a fourth. But at the same time, these researchers were doing studies, and they have hormonal measurements from fin whales. They picked up the feces using fishes and nets and feces-smelling dogs, and then studied that and observed a significant drop in the cortisol level, which is a stress hormone. So the animals are in the noisy environment, but the presence of shipping and the increase in shipping is certainly raising, there's observations that it's raising their stress level. So that's one of the reasons we care. The other is limiting their communication distances and their ability to hunt and navigate, which are hard to quantify. So let's talk about modeling ocean noise. Actually, these might be slightly in the wrong order, but I'm going to show you a impact of COVID, where there's also a significant drop in the numbers of ships due to reduced economic activity. Spire provided the AIS data. AIS is a global positioning beacon for each ship, and we have the March, April for 2019 and 2020. The acoustic model was run from every source out at 50 hertz, and then we've molded them together to get the ocean soundscape. So we're going to start with April 2019. This is a snapshot, so every dot you hear is an individual ship. We've run from the ships out, and let me use the mouse and show you some things. One of the things you see is that, again, it's super quiet in the South Pacific. This is shipping only, so there's no wind on this. And then when you get further into the northern latitudes, there's a lot more ships because of the US-Asia connection and the US-European and Europe through the Med to Asia. And so but the other thing that happens is the polar surface temperatures are significantly colder because of the climate and the distance from the equator, and sound travels better in those regions. It stays off of the seafloor. So part of what you're seeing here is a large number of ships, but another part you're seeing is significant propagation effects. In the South Pacific, there's very poor propagation. You can see that here. If we go to the average of the month, this is the entire month of April average for 2019, now you start to see shipping lanes. There's several lanes from the Cape of Good Hope up to Brazil, across to Buenos Aires, and then south. You can see a shipping lane here along South America. In Europe, there's a really nice shipping lane here from Cape of Good Hope up to the Strait of Malacca. You also see very high shipping levels in the Bay of Biscay, off of France and Spain, as well as the Med. And there's lots of traffic going to Russia along the coast of Norway. So this was done for the April 2019 time period. And then the next plot is the April 2020, which is after COVID. There's one anomaly which will catch your eye, which is right here. There's a ship that sat there the whole time. It's probably not real, but it wasn't filtered out. Apart from that, you can see that the lanes narrow and there's significantly more blue and black between the two. If I go back and forth, if you take a spot and focus your eye on it, from 2019 to 2020, there's an observable drop in the noise level across the board. I should also point out that the dynamic scale here is in decibels per micropascal squared, but it's 50 dB of dynamic range. So the dynamic range is huge. If you're seeing anything, it's a notable drop. I'll point out a couple places. One, there's a lot less ships going around the Cape of Good Hope. Strait of Magellan from the Good Hope. There's a region. And anyway, so if we do a difference map, we see, and this is now plotted of every place with color. This is the difference, the reduction in sound due to the lack of shipping and COVID. And so one of the things you see is it's kind of dominated down off of Antarctica, where there are very few ships, and so that's not particularly relevant. What is important is, the wide swaths of area where here in the central North Atlantic it's significantly quieter. It's a lot quieter north of Halifax and Nova Scotia. And this is the European-US shipping lane. North of Hawaii, there's a large region that is quieter. South of Australia, it's significantly quieter. This is the difference between April 2019 and April 2020. So the global average on this was about 3 dB, which is, again, is a doubling. So there's between 2019 and 2020, there was a halving of the acoustic energy in the global ocean. And so what that means, though, is that if you're a marine mammal and you can hear another marine mammal at 20 kilometers, if you reduce the level by half, that would allow you to hear another animal at twice the distance. So instead of 20 kilometers, it's now 40 kilometers. And that can have significant biological impacts. So here's a couple line plots from a few places in the Atlantic. The black is March 2019. Black is March 2020. Blue is April 2020. Red and yellow are March and April of 2019. And so this is the Bay of Biscay. You see in April, there's an observable difference in April compared to March as things really ramped up. But this is the Bay of Biscay, the Western Mediterranean, the North Sea near Norway, and then the central North Atlantic. So, at 3 to 5 dB or 2 to 5 dB average increase or decrease in the sound level. There's a few spots in the Pacific, particularly north of Hawaii. There's a very large signal. We're not quite sure why. Other places there are not big signals. Some of these were because of a small sample size and a movement of the shipping lanes. So let's move on to the shipping noise in the Arctic, which is a big issue. The Arctic Council through PAIM and the World Wildlife Fund have funded a study to look at shipping noise levels between 2013 and 2019 and the impact of the reduced sea ice due to climate change. And so we've been modeling this. We just started. The results will be hopefully presented to the Arctic Council in January or February. So the shipping noise will be modeled from 20 hertz, which is the frequency of fin whale and blue whale transmissions, all the way up to 10 kilohertz, which is where narwhals and dolphins communicate. So the plot on the left is the AIS data from just a snapshot of the data or actually a year average of the data from PAIM. It's the Arctic shipping data. It's the Arctic ship traffic data set. We'll be using that to say where our ships are. It's been filtered, and we're looking primarily north of Iceland in the Bering Sea, Barents, and et cetera. So here's a sound map of sound for the first week of September in 2019. If you follow the map, this is the ice line. It's not a minimum year, but it's significantly down. And we've studied basically the Barents Sea, the Davis Strait, and the Northwest Passage. This is the Beaufort and Chukchi, and then this is the Bering Sea. And so lots of traffic around Norway up here, through the Russian coast, along the Russian coast, and then a lot of traffic, a lot meaning 4 or 5 ships in 1 week through the Bering Strait. And you can see that over here. The model is run on, and that's what the little dots are for. But everywhere you see, there's a significant rise in the noise level over ambient sound. Here's the traffic lanes through the Bering Strait. These are Russian ships, and these are American, presumably. And it's much louder in the western Bering Sea, where it's deep water off of these Russian ports. This is where the marine mammals are, in the shallow water on the shelf, and sound doesn't travel very well there. So if we look at a couple blowups, the left is the Bering, Beaufort, and Chukchi. It's the same model. Here's the deep water. You can see the propagation. 90 dB, 87 dB average sound level. That's 30 dB above wind noise. And then up here you can see that the deep water in the Beaufort has an increased level. In the shallow water, ships need to be pretty close to you for marine mammals to hear them. In the Northwest Passage, now you see ships going through really constrained waterways. It's significantly noisy there. This is Davis Strait and Baffin Bay, and this is a lot of servicing of the Mons and the population in Greenland. So we're doing this work for the 6 years, for all seasons. There are about 600 ships in the Arctic in September. That number drops significantly when the ice in midwinter. So to conclude, the ocean is a noisy place. Animals have used this for group communication, food localization, and navigation. Some of that we observe and can define quantitatively, others we postulate. Man-made sounds are a significant portion of the ocean soundscape, and it likely increases the stress, and it severely limits the animal's ability to use sound. This is called masking, when they can't do what they want to do, they can't hear as they need to due to increased man-made sounds. And again, as climate change increases and it induces Arctic sea ice melting, this will open up the Northwest Passage for more months and more seasons, possibly all year round, and the sensitive ecosystem in the Arctic could be at risk due to shipping noise. So thank you for your attention, and that's it.
Thank you very much, Dr. Heaney, for that discussion on ocean noise. It's always been interesting to me that we don't normally think of noise as a pollutant, but it really is. It is something that we as people put into the environment that is harmful for the environment and the organisms that live there. So thank you very much for that discussion, Dr. Heaney. For our next topic, we'll be discussing overfishing with another renowned expert in this field, Dr. Karina Marakovich. On a personal note, Dr. Marakovich was actually my undergraduate academic advisor at the U.S. Coast Guard Academy way back in the day. Now, Dr. Marakovich is currently a professor at the Coast Guard Academy, where she teaches fisheries biology, fisheries management, and atmospherics and marine science. She is the chair of the Education Committee for the Southern New England chapter of the American Fisheries Society and a faculty fellow for the Goodwin Nearing Center for the Environment at Connecticut College. Karina has an MS and PhD in fisheries science from Oregon State University. Go Beavers. She was born and grew up in Sao Paulo, Brazil, and studied oceanography at the Universidade do Estado do Rio de Janeiro. Her research draws from fisheries and environmental sciences, maritime security, and scholarship of teaching and learning. Thank you very much for joining us today, Dr. Marakovich.
My name is Karina Lawrence Marakovich. I'm a professor of marine sciences at the U.S. Coast Guard Academy. One of the areas of concern for ocean conservation is overfishing. On this globe, you can see that based on Global Fishing Watch data, commercial fishing is concentrated on the coast of many countries where upwelling brings rich nutrient waters to the surface, which combined with nutrients from terrestrial runoff allow for high primary productivity. Another area of high fishing pressure is around the equator, where equatorial upwelling also allows for high productivity. Currently, the Food and Agriculture Organization, FAO, of the United Nations, it estimates that 60% of the world fisheries are fully fished, and the latest data shows that at least 33% of the fisheries are actually overfished. So also looking at the globe and the data reported by the International Maritime Bureau, we note that there is a high incidence of maritime crime in Southeast Asia, the Arabian Peninsula, as well as the East and West African coasts, and most recent information of maritime crime in South America as well. The same areas where we also see a lot of fishing pressure. The problem is three-pronged: weak maritime governance, leading to overfishing, which in turn can increase maritime crime. Weak maritime governance means that countries may not have enough laws and law enforcement to deter overfishing and address depleted fishing stocks. Consequently, Earth's coastal waters are experiencing increased levels of conflict and social unrest, affecting both regional security and environmental stability. This leads to food insecurity and maritime crime. And this creates a feedback loop where more maritime crime creates instability in the country and more pressure to overfish, which weakens a country's ability to govern its waters. In West Africa, fish represent the single most important source of animal protein. It's a way of life for coastal communities. Our study focuses on Ghana and Senegal, where small-scale fishers have long dominated the fisheries sector, and to this day, between 80 and 90% of fishers in Ghana and Senegal use what we describe as canoes, like the ones on the bottom right, fishing up to 6 nautical miles and beyond. But the number, size, and technological sophistication of those canoes are continuously growing. Trawling vessels are often owned by foreign interests who, on the surface, appear to comply with local laws by registering their vessels locally and hiring a 75% local crew. Per-seine vessels, like the one on the upper right, are joint ventures between Ghanaian and Chinese, Koreans or Russians, and their landings have increased in the past couple of decades. Over the past decade, numerous studies have concluded that West Africa fishers are experiencing dramatic overfishing. For the first time ever, scientists and fisheries experts in Ghana are now speaking of a complete collapse of the fisheries sectors in 2020. When fishing vessels overfish, they also increase bycatch, which is anything that you did not target but end up catching. Some of this bycatch is discarded overboard, dead or dying, and leads to a complete waste of resources. It is widely accepted by many maritime strategists that food insecurity can lead to regional insecurity and maritime crime. In this map, we plotted data from the International Maritime Bureau on number of piracy, armed robbery, and other criminal activity in the past few decades in Southeast Asia, Gulf of Aden, Arabian Peninsula, and Africa. We can see the increased number of criminal activities such as pirate attacks in West Africa, including Ghana and Senegal, in most recent years. Poorly managed fisheries do, in fact, directly and indirectly lead to a greater, more insidious criminal activities and a general weakening of maritime security. This manifests into violent attacks by foreign industrial vessels on domestic artisanal vessels, illegal fishing, forced labor and slavery, territorial disputes, and the use of fishing vessels to traffic weapons, drugs, and other illicit goods. IUU fishing, or illegal, unregulated, and unreported fishing, is a comprehensive term that refers to a variety of activities that violate or are unregulated by the conservation and management measures established under international and national laws. Approximately 37% of fish caught in West Africa is considered illegal or unreported. And there are different types of illegal activities, including dynamite fishing, the illegal use of monofilament nets. But I want to bring your attention to psycho fishing, where the large foreign-owned trawlers catch species that they are not permitted to land, so they work with the artisanal fishermen who adapted their vessels, such as the one on the bottom right, with an empty compartment to buy the fish from the large trawlers to be sold illegally to the local communities. Under Ghanaian law, the minimal penalty for a vessel caught transshipping fish is $1 million. Yet psycho fishing has become so profitable that it's extremely pervasive within Ghanaian fishing communities today. In fact, these psycho fishing canoes may also be involved in other maritime crime activities such as drug smuggling, weapon trafficking, and human trafficking to and from the foreign fishing vessels. One way to alleviate the overfishing problem is by not allowing fishing to occur during the most productive season. Senegal's closed fishing seasons have been relatively successful compared to many similar attempts throughout West Africa. On the other hand, Ghana has had several unsuccessful attempts, one more recently this year in May. Some studies highlight the ecological benefits of closing the season to give the fish a break to reproduce and generate large fish yields. And other studies point to the negative economic effects for fishers that rely on fishing for their primary source of income. Closed fishing seasons are not favored by fishermen, as you can see on the sign on the right. No fishing, no vote. All this leads to what Garrett Harding has characterized as the tragedy of the commons. In terms of implications, at the center of this complex problem, we have increased human population, creating greater demand for seafood and more pressure on the environment. Marine pollution and climate change have impacted the environment in many ways, as discussed in this plenary, exacerbating the situation by changing the species composition and distribution in the ocean environment, all of which increase food insecurity. Fishing overcapacity is one of the most leading causes of this overfishing. This means that we have too many people, too many boats catching too few fish. As fish stocks decline, there's a pressure to fish harder, sometimes illegally, leading to the collapse of fish stocks. This is not only an ecological challenge, but also socioeconomic issue, since 35% of the world's population gets most of their protein from ocean resources. Overfishing, caused by greater demand for seafood due to the increased human population, has led to larger boats using greater technology, fishing legally or illegally in their own country waters or outside their exclusive economic zones, leading to more bycatch. All this can change the natural food web of the environment and also increase the impact to the sea bottom. The large fishing boats sometimes drag nets or large dredges along the bottom, which destroy the habitat. When fishermen don't have enough catches, they don't have enough food or enough money to buy food, so that increases food and regional insecurity, which increases the pressure to overfish. So there is a feedback loop. Desperate fishermen use violence when competing with each other for fishing spots. They can start resorting to criminal activity to support their families, such as armed robbery, human trafficking, to transport young children to work as slaves in boats. And they use their boats to traffic drugs. In the absence of effective maritime governance, state and non-state actors can engage in or support piracy, illicit commerce, illegal fishing, support acts of terrorism, while exploiting a country's territorial waters and exclusive economic zone. Poorly governed maritime spaces also invite undue influence from predatory states, seeking to exploit a country's fisheries, energy, and natural resources. This is a very complex issue which demands holistic solutions through scientific research, monitoring fish populations, cooperation between countries and within communities to enforce fisheries laws and programs to provide alternative livelihoods to impoverished communities. So what can you do about this? You can make a difference through your actions and your voice. Become informed about scientific research regarding the ocean and your environment. The future of the ocean relies on your ability to understand environmental issues and to do something about them. Support policies for environmental protection, such as the development of marine protected areas, marine reserves, where fish and habitats are protected and allowed to recover from overfishing and habitat damage. These MPAs provide a safe haven for species to grow as they start spilling over into other areas where fishermen can catch them sustainably. Reduce your carbon footprint by biking or walking to school and to work whenever possible by recycling and using less electricity. There are several apps you can have on your phone to check which types of seafood are caught sustainably using environmentally friendly gear and catching species that are not overfished. In many countries, women are often marginalized groups who do not participate in the decision-making process, but they're essential to sustainability of fishing. So advocate for social justice, where people are treated with respect, are given a fair chance to have a healthy life, and are involved in a decision-making process about their environment.
Thank you very much, Dr. Marakovich, for bringing us home with that talk on global overfishing. Overfishing is another one of those challenges facing the world ocean that I find myself extremely passionate about because I really do believe that it's solvable in our time. So thank you very much, Dr. Marakovich, and thank you to all of our speakers. In summary, today, during our session on human impacts on the ocean, we discussed the top 10 challenges facing the world ocean today and what each and every one of us can do about it. These challenges are ocean acidification, global ocean warming, sea level rise, sea ice loss, coral reef loss, ocean deoxygenation, mangrove deforestation, ocean plastics, noise pollution, and global overfishing. Each and every one of these challenges seems daunting at first, but when we take it apart and discuss every one of these issues separately, each and every one of them becomes solvable. And I want to thank every single one of our speakers today for discussing these issues, explaining the science to all of us, and telling us what we as individuals can do about it. Thank you very much to our speakers, and thank you very much for tuning into this session. Thank you.
Thank you, Chris, and all of your presenters. This was an amazing session, and I suspect many of the presentations by your group will be used by geography teachers around the country when they discuss these issues in their classes. Thanks again. And now we're grateful to a group that has supported our symposium for several years. The Global Environment Facility, the GEF, is the largest multilateral trust fund supporting environmental action in developing countries and the main financing mechanism for multiple United Nations environmental conventions. Just recently, the GEF appointed a new president, and he is with us today. Carlos Manuel Rodriguez, the former Costa Rican Environment and Energy Minister, is an internationally recognized expert in ocean conservation, and it is a real pleasure for me to be able to welcome him today to our symposium. President Rodriguez.
I've been an ocean lover all my life, starting with swimming on the beach with my family, later surfing and diving. Like most kids, I wanted to be a professional surfer when I grew up. I became something better, an ocean conservationist, establishing marine protected areas and other initiatives in Costa Rica as Minister of Environment, and now around the world as the CEO of the GF. Oceans are amazing, full of life, mystery, and escape. Why then it is that these ecosystems are such a extreme threat? What it is that it is difficult to abate these threats? I'm a conservation warrior. My whole career, since a park ranger to Minister of Environment to now CEO of the largest founder of conservation initiative, it has been clear. The ocean being remarkable, beautiful, and unique is not enough. As Minister of Environment, every day I had to battle over limited financial resources for new legislation with other ministers who were fighting illiteracy, poverty, poor health care. As a matter of fact, I always was surprised by the fact that the Minister of Finance never understood that we at the conservation sector provide human well-being and economic growth. If we are to succeed, we have to sell ocean conservation not just in terms of what we are losing, the endemic species, beautiful reef, pristine wetlands, but in terms of what we gain by having healthy oceans and preferably in economic and social terms such as wealth and jobs. So here are my top selling points for ocean conservation. Oceans, they create jobs and economic growth in sectors ranging from tourism to fisheries. They provide recreational enjoyment, beach walks, surfing, diving, recreational fishing. They provide the seafood that we all enjoy. They protect our shorelines and sequestrate carbon to mitigate climate change. The importance of promoting this economic and social benefit of ocean conservation is a lesson I learned as a minister and I'm bringing to the GF, where we are investing nearly $100 million every year in ocean and freshwater conservation to address the biggest challenges facing ocean health, which are land-based pollution from plastic, sewage, and toxic discharges, other overt destructive fishing practices, and habitat loss. But $100 million a year investment isn't enough, which is why my mission at the GF is to scale up through partnerships. We are reaching out more than ever to other key players in the philanthropic community, as well as multilateral development banks, and even the private sector. But success isn't just about the financing, it's about action. And that also where we need to scale up partnerships by working not only with the academics, scientific communities, NGOs, and government agencies. It also requires partnership with the unusual suspects, businesses in particularly, to use the arguments I just described to shift toward sustainability and sustainable practices. It is in the interest of hotels to ensure beautiful beaches for their guests, and fishers want healthy fish stocks as insurance for the industry. Working across countries is also a fundamental part of our partnerships. At the GF, we are bringing together countries around shared large marine ecosystems all over the world, from the Humboldt Current large marine ecosystem in Latin America to the Bay of Bengal in Asia, to the Canary Current Lime in Africa. Through these partnerships, we're working on measures to address the major threats, including coastal and marine ecosystem protection. With a CBD goal of 10% by 2020, NPAs are a priority of many governments. At the GF, this is a top opportunity. In fact, we recently approved $22 million JEF funding for the Blue Nature Alliance, with $100 million co-financing, which will result in 1.2 billion of hectares of new or improved marine protected areas. Fostering sustainable fisheries is another top priority that we are addressing, from near-shore waters to the high seas. For example, we currently have a global coastal fisheries initiative with national projects in West Africa, Latin America, Southeast Asia, while we also have invested in high seas fisheries management over the last 6 years. Finally, pollution abatement has been a priority throughout our history and has included addressing nutrient eutrophication, everywhere from the Black Sea to the Bengala Current, and we have expanded into addressing plastic pollution with projects in West Africa, Southeast Asia, and Latin America. I hope this presentation has given you an appreciation for the benefits of the ocean conservation, the major threats facing these valuable ecosystems, and the solutions for long-term conservation based on strong and solid partnerships. This conference provides a great opportunity to recognize the important role of science that plays in conservation and the need to ensure equal access to information if we are to build a strong, functional interface within science and policy making. As you engage further in this event, I encourage you to consider opportunities for partnerships, and I urge you all to seek out the unusual suspects to unite for ocean conservation. Thank you so much.
Thank you, President Rodriguez, for all the work you're doing for the oceans and beyond, as well as your support for AGS. You can count on us to partner with you. And now, AGS President Marie Price will interview Enrique Sala about his new book. Marie?
Dr. Enrique Sala is an unusual combination of scholar, activist, and storyteller who will share his passion for the ocean and its varied life forms in today's talk. This summer, he published The Nature of Nature: Why We Need the Wild, a smartly written book based on his vast field experiences. The book explains how the natural world works, how humans are unraveling these processes, and what steps we can take to improve matters. Born in Spain, Enrique studied ecology in Spain and France, earning a PhD from the University of Aix-Marseille. He then taught at Scripps Institute of Oceanography in California for several years, but left his academic post when he concluded that, quote, "I was describing how ocean life was dying with more and more precision, but not offering a cure." Since 2008, he has been an explorer in residence at the National Geographic Society. One of his major accomplishments at NGS is leading the Pristine Seas program, which aims to expand the number of protected marine areas around the world. Thus, we could think of no better contributor to Geography 2050 than Dr. Sala. Enrique, welcome to the conference. We're so happy to have you here.
Thank you so much, Marie. It's a pleasure to be in the cyberspace with you.
Before we begin our discussion, I'd like to introduce the book and Enrique a little bit more with this short video.
Too few who can feel, I am the sea, and the sea is me.
Growing up in Catalonia in the 1970s, every Sunday I would sit in front of La Caja Tonta, the dumb box, watching my hero, Jacques Cousteau. The exotic places, the daring underwater explorers, the spectacular creatures. It was all I wanted to do with my life. And sometimes dreams do come true. Now, I've traveled the world many times over, falling in love with nature over and over again. Following in my hero's footsteps. But a lot has changed since Cousteau's time. In 2019, I explored nearshore waters of Costa Rica. The unprotected areas where Cousteau might have found a thriving ecosystem were barren. A few small fish and no sharks. The top predators that should be hunting here, like lions in the savannah. What nature has taken millennia to create, we humans have destroyed in only a few generations. Here, I could be anywhere on our planet where life isn't protected or valued. These beautiful places are incredibly fragile. And without them, we will not survive. I am Dr. Enric Sala, a National Geographic explorer, and like many of you around the world, I have been spending my time at home to help stop the spread of COVID-19. The pandemic has been keeping me from doing what I love, exploring the ocean. 12 years ago, I started the Pristine Seas project at National Geographic, which uses a combination of research and media to help convince government leaders to create marine protected areas in their waters. The need to protect our wild places on land as well as underwater couldn't be more urgent. To understand why we are suddenly at a crossroads when our grandparents' generation seemed to live in a time of abundance requires some quick historical perspective. The way we fished, farmed, raised livestock, and developed the land was, for centuries and even millennia, done at a pace that did not have global consequences. But everything changed with the Industrial Revolution. In just the past couple hundred years, we got so good, so fast, at extracting these same resources at scales once unimaginable, that the consequences are biting back at us. Those of us who study these connections see again and again that where biodiversity is destroyed, ecosystems break down, with unintended and disastrous consequences. In the eastern United States, humans hunting the gray wolf to extinction caused a chain reaction that likely led to the epidemic of Lyme disease that persists to this day. The devastating Indonesian tsunami of 2004 was made far more destructive because of the cutting of mangrove forests, which normally act as a shield, buffering the impact of storm waves. In the Line Islands in the Central Pacific, the waters in overfished areas were filled with pathogens, including bacteria like Vibrio, which can cause cholera in humans. Bottom trawling the seafloor, clearing forests in the Amazon, and melting permafrost in the Arctic are all releasing tons and tons of carbon into our atmosphere. And in Wuhan, China, a virus that would have dispersed itself naturally in a biodiverse environment instead made its way to humans, likely from bats, animals whose habitats have been systematically raided and destroyed for decades. These examples just scratch the surface of how humanity's reckless relationship with nature has had disastrous effects. My life has been dedicated to figuring out how we can have thriving natural ecosystems and resilient human populations together. What I found is nothing short of miraculous. Remember the desolate waters I explored off Costa Rica? Well, just 10 miles from the coast is an island called Isla del Caño. The difference is stark, and it's no accident. Here, the waters are fully protected. No fishing to stress the ecosystem toward collapse. Natural checks and balances keep predator and prey in a sustainable balance. It's a strong, resilient, constantly regenerating environment. the abundance of marine life spills over invisible boundaries, creating more catch for local fishermen, food security for communities, and increased tourism revenue from world travelers who want to experience these treasures firsthand. This one truth is at the heart of my life's work, where biodiversity is allowed to flourish, healthy ecosystems thrive, and we all benefit. Protecting intact ecosystems works because it allows nature to do the hard work for us. Our natural world can be a sustainable, resilient engine of regeneration. We just need to give it some space. Reintroducing wolves to Yellowstone National Park in the 1990s caused a positive cascade throughout the food web, leading to a return of plants and animals of all kinds, creating a more diverse and balanced ecosystem. During a cyclone in Mozambique in 2019, the Gorongosa National Park absorbed the rainwater equivalent of 800,000 Olympic swimming pools, protecting many populated areas from the worst of the flooding. In the pristine southern Line Islands, giant clams are abundant. These incredible animals, which are overfished in much of the Pacific, are like the N95 masks of the coral reef lagoons. Like other marine animals, they filter bacteria and pathogens, including Vibrio, out of the water. And leaving wild animals in the wild and their habitats intact helps to keep viruses from arriving on our doorstep. So on top of providing us with oxygen, food, carbon sequestration, recreation, and spiritual inspiration, nature is also shielding us from disease and natural disasters. My team and I have spent over a decade bringing this message to world leaders and decision makers who have the power to change policy and create protections for nature. 1 year after I came to Washington, D.C. to launch Pristine Seas with National Geographic, I found myself sitting in the White House as the President of the United States signed a proclamation creating the Pacific Remote Islands Marine National Monuments, one of the largest marine reserves in the world. I couldn't believe that our research, our images, our stories about that place helped to inform one of the most important ocean policy decisions in the history of the United States. But my next thought was, we can do this again. 12 years later, we've done this 22 times. We've helped to protect almost 6 million square kilometers of ocean. And we can do the same on the land. We must protect the critical wilderness areas we depend on. Our target is ambitious, 30% of the planet protected by 2030. But Pristine Seas has proven that thinking big can pay off. I dream of the day we can all be in nature again, perhaps with a deeper understanding of its importance. It's not too much to say that if we protect nature, she will protect us as well. That's life in balance. That's why we need the wild.
All right. Question 1, you ready?
I am ready.
In The Nature of Nature, you make the case that we need to expand protected places on land and in the ocean for economic, biological, and even moral reasons. Given that the future of the world ocean is the theme of Geography 2050, we'll focus on marine environments in this discussion. You outline the concept of keystone species, which are species that, if they are removed, the biological community changes dramatically, becoming less diverse. What are the keystone species that you focus on when assessing the biological health of the oceans, Enrique?
Yeah, imagine that you go to a coral reef and jump in the water. If you see sharks immediately, that means that that coral reef is in good ecological health. We need the top predators because most keystone species are the top predators on top of the food web. But they don't all need to be large like the sharks. They can be little and cute like the sea otters on the Pacific coast of North America. Sea otters love to eat sea urchins, and sea urchins love to eat kelp. They are like underwater lawn mowers. If their abundance is really high, they can turn kelp forests, these giant kelp forests, which are like the redwoods of the sea, they can turn them into barren grounds, just eating everything away. So you have the sea otters eating the sea urchins, means that there are very few sea urchins. The kelp can grow and provide the home for all these other species of plants and animals that are living there. This is why we need that keystone. The sea otter is like the stone on top of the architectural arch that keeps it together. If you remove that stone, the entire arch collapses.
I like that metaphor a lot. Enrique, you're probably one of the few people that gets excited when you jump into the water and see sharks. But in addition to sharks, you make a convincing case that whales help fertilize shallow water by releasing iron in their feces that promote phytoplankton, which support krill and other species, which led me to wonder, how are whale populations today, and are there marine areas where they are adequately protected?
Yeah, whales are still recovering from the industrial slaughter in the 20th century and before. In the 20th century alone, man killed 3 million whales around the world. And these animals, these huge consumers of plankton, they can eat deeper. Like a sperm whale, for example, they can eat a giant squid down to 3,000 feet, and then they come back to the surface. The big whales, the baleen whales, like the blue whale or the humpback whales, they eat plankton and very small fish and krill. And yeah, as you said, krill has iron in their tissues, and as the whales eat and then poop part of the iron outside, they fertilize the shallow waters. Without whales, the open ocean would be a desert, and they help to fertilize, they help to bring life. Unfortunately, the most whale populations haven't recovered to historical levels. Now we're talking maybe about a few 100,000 whales around the world, when they used to be millions. So we still have a long way, and some of these species live very long lives, 50, 60, 70 years. In the case of the bowhead whales in the Arctic, they can be more than 100 years old. So it's going to take a long time to bring them back.
I grew up along the coast of California, and I remember seeing the whale migrations going north to south, and it always was a beautiful sight to see them. I do think humans, though, we humans have a terrestrial bias when we consider conservation. It's easier to walk through a forest and recognize what happens when it's cut down than to appreciate what happens to the seafloor after an industrial trawler has been dragged across it. So how do we increase this understanding of marine ecosystems so that people recognize the negative impact we're having on the oceans, and that healthy oceans are vital for our survival?
It's more difficult than going to a forest, right? Everybody can walk in a forest, but not everybody can dive or get in a submarine and see the damage. So we have to bring that world to them. This is why we at National Geographic and Pristine Seas, we bring these places to people and to leaders so they understand how unique and rich and wonderful they are. And also we need to show the damage. When I was a professor at the Scripps Institution of Oceanography, I thought that having scientific papers would be enough, right? The political leaders, decision makers will look at the scientific data and make decisions based on this, but clearly that's not the case. And so we need to make it emotional, And there is a wonderful example right now on Netflix. That is this latest documentary by David Attenborough, "A Life on Our Planet," and it's his story, his personal story, his life story, how he saw life from thriving to being depleted all over the world, and why this is such an existential crisis for humanity, and what we need to do to fix it. So I think that the data are not enough. We need to put a human face so people will relate to.
You tell a wonderful story in the book about how you worked with the president of Gabon, taking him out on a ship and having him run a rove. And in that process of the rove navigating on the seafloor, a troop of really large dogfish groupers were staring into the rove. And this just excited his imagination and appreciation for his territorial waters. So I'm asking you, is providing world leaders such firsthand exposure, is that an effective conservation strategy?
Oh, absolutely. There is invariably, if you take a leader to a wonderful natural place, be it a tropical forest or a natural grasslands with lots of herbivores, or a kelp forest or a coral reef, invariably they fall in love with it. Well, I can think of a few politicians right now in the US who would not be impressed by nature, but the rest of the world, the rest of humanity would. And you can see their faces. It's like they become children again, because we have what E.O. Wilson calls biophilia. We have this innate love for the natural world. We have this craving, this desire to be out there. And the pandemic, right, the COVID pandemic has made it very clear. Everybody wanted to be out. Everybody was fascinated by these videos of animals coming back to cities or near our shores. So absolutely, first-hand experience, first-hand exposure to wonderful natural places is the best way for leaders to fall in love with these places. And once they fall in love with them, intuitively, they know they have to do something to protect them.
Mm-hmm. Making an economic argument that protected areas will increase the availability of marine resources in nearby areas that are not protected seems like a win-win situation. Yet the evidence is not always persuasive, as you found out in talking to people. So how do you convince the skeptics, say a minister of fisheries in a developing country, that protecting areas is good for business?
Yes. We have so many examples. This is one of the trickiest things we do, right? Because we have the data, we have the science, we have the economics. So the facts are very clear, right? But fisheries is one of the most corrupt sectors on the planet, especially industrial fisheries. The coastal artisanal fishermen, that's a completely different world, and many of them have a great understanding of their environment. But the big industrial fishing fleets, like these super trawlers that are 360 feet long, nets so huge that they could fit a dozen 747 jets in them. One pass of the net destroys deep coral reefs that are thousands of years old. And these guys don't have any regard to about nature. They are there for the short-term profit. So in many cases, they are in cahoots with the fisheries departments. And fisheries departments are some of the most corrupt departments in governments worldwide. So how to break that? Well, one way is exposing the illegalities of industrial fishing, showing to the country, to their fellow citizens, how they are collapsing their fisheries and harming their livelihoods. And in some cases, when you're dealing with a few good ones, you have to provide the right incentives, right? It's not just showing the scientific data. But yeah, we are having a hard time always with the fisheries ministers, because they side with industry, which, despite the lip service to sustainability, continue over-exploiting the ocean.
Mm-hmm. One of the great things about your book is that even if you're an oceanography expert, you're going to learn things. So I think most of us can imagine that the oceans are places that are polluted with our plastics and oil spills and dumping. But reading your book made me aware that there's a problem of acoustic pollution in the ocean. So how is increased noise damaging to marine life? And are there any guidelines surrounding acoustic pollution?
There are a few ways acoustic pollution, increased noise in the ocean affects marine life. Of course, the most evident is whales. Whales and dolphins use noise to communicate underwater, like the beautiful humpback whale with these eerie songs that can propagate for hundreds of kilometers because they sing in low frequency. They have songs that change from year to year and between populations. They have this singing culture. It's extraordinary. Of course, when you add seismic testing, which produces these explosions every few seconds for days nonstop, basically destroys their hearing system, destroys their communication system. Also, the increased noise of cities and shipping in some coastal areas is making it very, very difficult for the whales to be able to find each other, to reproduce with each other, which only harms their ability to replenish. And then there are other things like, for example, little reef fish that live in the coral reef and they reproduce, they release eggs and sperm in the water, and then the eggs hatch, the larvae float for a while, and then when the fish larvae are large enough, then they come back to the reef hearing the noise of the reef. Right? When you add all of that noise pollution, like outside the Great Barrier Reef, for example, with these huge cargo ships that transport coal from Australia to China, all that noise is making it very difficult for the fish to be able to hear the reef and replenish the reef. So there are all these effects that we didn't think about that propagate like the sound across the ocean.
You know, in the symposium, we'll have a session that deals with patrolling the seas, which is a challenging task. Designating a protected marine area, which you have advocated, is only the beginning of a process. Who are the monitors of protected areas, and how effectively are marine protected areas actually protected?
The countries of the world, the governments are the monitors. Most of the areas protected in the world, like 99% of the area protected in the world, is within the 200 miles exclusive economic zones of countries. It is countries that decide which areas to protect, and they have the responsibility for monitoring them. We have tens of thousands of marine protected areas today, and about 7% of the ocean is in areas that have been designated or proposed for protection. But less than 3% of the ocean is in areas that are fully protected from fishing or other damaging activities. And most of the marine protected areas are not well managed. Many of them don't have a management plan, they don't have a budget, they don't have personnel. And what's still worse, there are some areas, like in the United Kingdom, where trawling is allowed, including by super trawlers, these ships that are more than 300 feet long. So most of the protected areas we have in the world are kind of a joke. They are just lines on a paper. But the good news is that when they are well managed, they work very well. I have seen it. I have seen it with my own eyes. That you protect them and marine life recovers spectacularly.
Yeah, I noticed that Canada has recently expanded its marine protected areas, and I guess it is not just designating them, drawing lines on the map, but actually having a management plan that will make a big difference. I want to end now with the Pristine Seas program. It's an ambitious goal, protecting 30% of the ocean by 2030. As you said, fully protected areas are pretty small, but there are places at least designated on the map. Can you tell us about this program a bit, its impact, and how our viewers can support its work?
Pristine Seas, I started Pristine Seas in 2008 when I quit academia and moved to National Geographic to work on the cure that you mentioned before. And we combine exploration, research, media, and policy work, working with communities to inspire governments to create these large marine protected areas, these areas that protect some of the last wild places or the wildest places left in the ocean before it's too late. And what we are doing is a contribution to that global target of 30% that you mentioned. This is something that the science is converging on. We are at National Geographic, we are working with the WIS Campaign for Nature on this target because we have an opportunity next year. Next year in China, there's going to be the conference of the parties, the COP15 of the UN Convention on Biodiversity. That's the time and the place where the countries of the world are going to agree on how much more nature, how much more space we are willing to give to nature. Right now, we have 7% of the ocean in some kind of protection, 15% of the land. And the science is telling us that if we want to prevent the extinction of 1 million species and the collapse of our life support system, if we want nature to continue help us absorbing our carbon pollution from the atmosphere and helping to mitigate climate change, we need at least half of the planet in natural state. So this 30% by 2030 is a milestone, is an absolutely necessary and unnegotiable, I would say, milestone. And there are already 32 countries in the European Commission that have supported this, that are supporting this. So we hope to get to China next year and have the world agree on doing what's right for not just for nature, but for ourselves.
Enrique, thank you so much for your time today and for the work you're doing on behalf of all of us. It's so important. A link to the book, The Nature of Nature, Why We Need the Wild, is available on the website. And Enrique, I hope you return in 2030 so we can do a follow-up and see that 30% of the marine areas are now protected.
A deal. And Mary, thank you so much for having me. And I hope that I'll be able to see you in person way before that.
I certainly hope so. Be well, and let's keep fighting for our marine areas.
Thank you.
Thank you.
Thank you, Marie and Enrique. If you want to order Enrique's book, you can do so by going to geography2050.org and click on the bookstore button.
Hello, I'm Marie Price, President of the American Geographical Society. We are so pleased that you were able to join us today for Geography 2050, and especially for this session on human impacts on the ocean. AGS is pleased to bring this event to you free of charge, but this costs money, and if you could make a small donation, that would make a big difference in us being able to do Geography 2050 next year and the year after that. Thanks again.
Thanks, Marie. AGS is no stranger to ocean research and exploration, and there is no one more qualified to explain our long commitment to the ocean than our President Emeritus, Dr. Jerry Dobson. Jerry?
Hi, welcome to Geography 2050, the future of the world ocean. I'm Jerry Dobson, President Emeritus of the American Geographical Society. I want to talk with you today about the American Geographical Society's long history of involvement in oceans, ocean science, and oceanography. The word oceanography did not exist until 1859. We were formed in 1851. And from 1854 to 1869, AGS was a world leader in what was called then the physical geography of the seas. AGS counselors themselves were instrumental in studying the oceans, shaping ocean science, and formulating oceanography. Let me illustrate with a 15-year vignette of the American Geographical Society focusing on the officers and council. This is a period leading up to the completion of the transatlantic telegraph cable, which we were heavily involved in. We had on our council Cyrus W. Field, who was the developer of the cable, the transatlantic cable. We had Matthew Fontaine Maury, who was the greatest oceanographer of his day, often referred later as the father of oceanography. There are others who have been given that name, but he was the earliest and had the strongest claim on it. He wrote a book called The Physical Geography of the Sea while he was on our council in 1855, and his specialty, his purpose his role in the transatlantic telegraph cable was to feel where to place it so that it wouldn't break frequently. And we had Samuel F.B. Morse, the inventor of the telegraph. Those three men conspired on our council to help produce the plans and eventual implementation of the transatlantic telegraph cable. If you look at a typical website in oceanography today and look at the components, you will see geography listed prominently. Conversely, if you look at a geography website, the oceans will be listed as one of the many places we study on Earth. Moscow State University has 15 geography departments within the Faculty of Geography. One of them is oceanography, called oceanology there to this day. Look around the world and you'll only find a few departments, schools, or colleges that combine geography and oceanography. Two of them are in Great Britain, one in Australia, and one in the United States. Later in the symposium, you will meet Don Wright, who used to be on the faculty at Oregon State University. AGS is still advancing the physical and human geography of the seas. We had a special issue on Oceans Connect back in 1999. We've had several articles since that are notable. We still honor oceanographers, ocean explorers, ocean scientists. The highest honor we grant is to allow explorers to sign our flyers and explorers globe. You'll find names like Louise Boyd, who used sonar, one of the earliest attempts to map the ocean floor, the sounds on both sides of Greenland. William Beebe, who set the depth record. Don Walsh, who set the depth record. And Sylvia Earle, noted ocean explorer today. Our Cullum Geographical Medal has gone to 4 oceanographers, ocean scientists in the past, and will be given to another, me, later in this gathering. The George Davidson Medal focuses on the Pacific Ocean, and it's been given to 2 geographers in the past and will be at this meeting given to Don Wright, geographer and oceanographer. In an article in 2014, I described Dawn as geographer and oceanographer, chief scientist of ESRI, and that she personifies the type of collaboration that will be needed between geography and oceanography. I will add today, so does AGS. Always has, always will.
Thanks, Jerry. By the way, don't forget to join us Thursday for our annual Honors and Awards ceremony, where we will recognize Jerry for his extraordinary lifetime of achievements and present him with the Cullum Geographical Medal. One of the most important government agencies involved with the ocean is the National Oceanic and Atmospheric Administration, which we all know as NOAA. Today, we're very eager to hear from the most recent acting chief scientist of NOAA, Mr. Craig McLean. Craig?
Good day. My name is Craig McLean, and I'm from NOAA, the National Oceanic and Atmospheric Administration of the United States government. I've been with NOAA since 1981 and I've seen quite a few changes, and I've had quite a few jobs. I'm a retired ship captain. I ran research vessels in the world's oceans, and I also conducted deep sea explorations and worked in the fisheries world. I've seen a lot of facets of this world and feel very appreciative of the opportunity that Dr. Tucker has provided for me to be presenting to you. In terms of the work that I do today, I'm responsible as the Assistant Administrator for Research of NOAA to be conducting climate science, meteorological science, oceanography, and coastal science. So we are responsible in the part of NOAA I handle for the research that looks over the horizon and looks to the future. And as you look at your future, or our future, of the world ocean that's coming forward, I think it's something that we need to spend some time on, and I appreciate the opportunity to share these views with you. So if I may have the next slide, please. The current status of our ocean is defined rather well in several documents, and I would like to acquaint you with them and give you brief highlights of them, but I commend these to you for your further reading and understanding. From the Intergovernmental Oceanographic Commission, which is a UN body, I represent the United States to that body, but the IOC, the Intergovernmental Oceanographic Commission, produces the Global Ocean Science Report. And here are some of the highlights from what we have in terms of the issues that are upon us that we're focusing on as we report the status of the world's oceans, just as we find it. So much as a geographer might quantify different parts of the Earth, we've quantified the different components in terms of marine ecosystems, their functions and processes. They are defined and evaluated in terms of their current state and current status. The oceans and climate, remarkably, the oceans are the driver of climate, and climate does have feedbacks on our oceans and the ocean ecosystem. These will have changes to our geographic distribution of species and ecosystems and components. Ocean health, it's quite a relative term. Some people could look romantically at the ocean as kind of a living and breathing patient. And perhaps if you do, you might be astounded to realize that while we can monitor the pulse and respiration of the ocean, we still don't have a Gray's Anatomy of the ocean. We today do not have a good map of the entire ocean bottom. That's an objective that we're going to get to very shortly, but that's something that we as a global society need to be contributing to. Human health and well-being. Science can describe for us the wellness factor of living on or near the ocean for humans. We get some sort of positive energy and state of wellness by doing so. And we also have direct human health insults, whether they be physical, from tropical cyclones, tsunamis, or other types of storms, to other kinds of insults where disease-bearing organisms can be impacting human health, such as harmful algal blooms or other types of human causations, and some naturally occurring, of course, but the more we pollute, the more we accelerate the frequency of these events happening. Now, blue growth comes up, and that's featured in the Global Ocean Science Report as well. Blue growth is a varied definition around the world, but by and large, everyone has really settled on the comfortable definition of trying to find a constructive pathway to utilize the resources of the ocean in a sustainable way, where those resources are available for tomorrow's generations, not over-harvested by today's. Then looking at marine geohazards, nearly every part of the Pacific is impacted by the Ring of Fire and the geology of the Pacific and very active plate motions. And volcanism has caused tsunamis and other impacts around the world. It's important that we understand that. Our friends in Japan are very focused on making sure that their country is well monitored oceanically in order to be protected and preserving their society's resilience to any further insults. And then lastly, the role of ocean technology. So a very good study. I ask you to immerse yourself in this if you feel motivated, and it gives you a very good shot of photograph, if you will, analogously, of where we are today in the oceans. Now let's move on to some of the other studies that I want to spend a little bit of time reminding you of. So this is the snapshot. This is where we are today. So next, I want to bring up the Intergovernmental Panel on Climate Change, the IPCC, and they've conducted a review and assessment on what would happen if we were able to limit global warming to 1.5 degrees centigrade. And that's the track that we have left behind. But it's a track that was a good benchmark. And a few years ago, it was where we wanted to be. So 1.5 degrees centigrade is something that will, in fact, have an impact on the biological communities, their distribution in the world, basically the ecosystems of the world, the food that we are dependent upon, are very, very much going to change even under a 1.5 degree very conservative change in global ocean temperature. Let me dispense with the obvious for a moment here. Our agency, particularly the part that I'm responsible for, of oceans and atmospheres, was created in 1970. We're 50 years old this year. NOAA's very proud to celebrate that. And upon our inception and our creation, we took a national study, a national policy study that was called the Stratton Commission. And Stratton Commission made recommendations to create NOAA. One of those creations was to study the impact of the ocean and the atmosphere. We knew that at the weather time scale, the oceans drove weather. We knew at that time scale there was an interaction that we could sense better because of the technologies that had been developed mid last century. Applying those technologies and studying the question for 50 years, we've come to conclude that the relationship between the ocean and the atmosphere is what today we call climate science. And climate science is real. There is no hoax in climate science. I venture to say the only margin of hoax would be in purposely funded deniers of climate, simply because people fear the policy impact or the potential economic impact of what recognizing the climate problem we're facing might have to say. So if you dive into this report at 1.5 degrees centigrade, you'll see some of the impacts that are currently upon us, currently forecast, and where this will take us through, for example, the end of this century, which for many people is within the domain of their lifetime. It's certainly within the domain of today's children's lifetime and certainly one's grandchildren. We should care about this. We do care about this. We're very responsible for contributing to these reports. Next slide, please. Now let's go to the National Climate Assessment. So we started with the 1.5 degree global. We now look at the national assessment. And here our agency is very responsible, along with other federal agencies, for providing a forecast to the nation as to what climate change, which is happening, is doing to our nation and where we might find the vulnerabilities, the stresses to our economies, and also the challenges to our human health, our well-being, and our economic prosperity. Once again, I think the fourth climate assessment provides a very stark warning that human causation is the major part of this, and it's on top of us right now, and we are seeing the effects, because if you look at what's happening today, they were rather accurately forecast 30 plus years ago when we started to look at this question in terms of modeling the future. We modeled the future correctly, and in many cases, what's happening today is worse than what we modeled back in the previous days that I refer to. So the fourth national assessment is something that's very informative. I commend that to any geographer's reading, or any citizen who wants to be responsible for their community and their planet. But most important, we're just undertaking now the fifth climate assessment. These are required to be produced by the Congress. We produce them every so many years, roughly 4 years. We're in that process right now, and we're ongoing to get the fifth assessment up and running. Next slide, please. This report really answers the question you asked me to address. I could spend an entire lecture on this, but I won't. What I will do is commend for your reading this very important study. This once again was produced by the Intergovernmental Panel on Climate Change, the IPCC, and it puts a rather stark warning for us based on the various climate change profiles that may await us. You can see in this report how the Arctic and other ice shelves are melting. They melt into the sea. They constitute sea level rise. The increase in ocean water temperature because of the heat absorption that is largely man-made and man-driven is causing sea level rise as well. When the sea level rises, we have coastal residents that are globally challenged for their very survival. We have nations that are looking at alternative locations to move and evacuate and basically be trying to find a way to survive in a world that's changing around us. This report also talks about the biogeographic distribution of marine resources, what we might know today as, for example, New England's in America, New England lobster and scallops. At some point in the future, those are going to be Canadian lobster and scallops as we watch latitudinal migrations, both in Alaska and in the New England coast, all over for that matter. We've seen and you will learn in this report of the changes in ocean acidification, where the carbon dioxide in the atmosphere, once absorbed into the ocean, changes the ocean chemistry, changes the pH of the ocean chemistry, and makes this ocean more acidic than it has been in millions of years. In fact, we're at a CO2 atmospheric concentration of roughly, as a global average, 412 parts per million. This world has not seen in 3 million years 412 parts per million. And something worthy of further note, we as a human species did not evolve in this environment. We evolved in an environment with far less CO2 in the atmosphere, so that our place in this ecosystem was one made available through evolution at a time different than the chemistry we're producing now for the atmosphere and ultimately the ocean. So there are many other attributes in this report, and I think it's worth looking into further, digesting and understanding. And there is a remarkable summary that puts matters in very confined brackets of proof. And they use terms wisely in the IPCC that a phenomenon is very likely to be happening. A phenomenon is happening with high confidence. A phenomenon is happening with very high confidence. So that the scientific conclusions that are offered in this and the other reports that I mentioned are well bracketed by a confidence interval without having to get into the details of statistics that scientists might be more familiar with, but that the lay public might find confusing and hard to follow. So we don't talk about 98% confidence intervals. We use these other terms to substitute for those. I certainly commend this study for your action. So if we can move to the next slide now, then please, let's put this in context. This is an often used slide, and I credit our friends up at the U.S. Geological Survey and Woods Hole Oceanographic Institution for providing it. This is a remarkable relative expression of how much water is the world's ocean, right? What does it constitute? And another analogy, if you look at that water droplet that's placed over roughly Kansas, Colorado, in the middle of the continental United States, an analogy would be, as one person explained to me, taking a basketball, dunking it in a body of water to totally immerse it, and then pulling it out. And the residual water that would stay on that basketball for the first immediate moment of its removal would constitute roughly the amount of seawater that's distributed around the globe. It's not a lot when you look at it with the size of the Earth. That now makes, to me, much more relevant the idea that I could be having an influence on that amount of water. You know, I grew up in a polluted river environment in New Jersey, very north of New Jersey. And I looked at that river and I contemplated how unfortunate it was that I couldn't swim in that river. But I also contemplated that I can understand how the people who live alongside this river can be polluting it, and therefore I can't swim in it. It made sense at that relative scale. When I consider the world's oceans and our human impact on the world's oceans, it makes it challenging until I look at this diagram and realize it isn't a huge volume of water, relatively speaking, to the global distribution that it's under. So just put that into your mind. It is not an insurmountable leap to conclude that we humans are influencing that volume of water distributed on planet Earth in the chemistry, in the physical distribution, and certainly in the biological distribution. Now let's turn to the atmosphere with the next slide. If you look at this rather thin envelope of gas that's roughly 60 miles thick, 100 kilometers, that's it. That's our atmosphere. And beyond that, we're in open space. Once again, given the scale and the size of planet Earth, that's quite remarkable. It's pretty lean. Once again, I can understand the scale and scope that I and the rest of the global population could have some influence on this thin envelope of gas and be changing the gaseous content with the production since the Industrial Revolution of carbon dioxide and other greenhouse gases that we are distributing into this atmosphere and are causing a change in our environment. So if we look at that now and go back to the oceans, science is pretty good. We've studied a lot. We've understood and concluded a lot with peer-reviewed verification. But one of the things that remains open and large is the ocean. So if you go to the next slide, I think you'd be astounded to realize that less than 95% of the world's ocean has really been surveyed, understood, mapped, diagnosed, characterized, or even far less a percentage has been viewed by human eyes. So when we look at what inspires us about the oceans, some of it is romantic, some of it is survival, and some of it is a productive necessity for food, for security, or for national security and well-being. But what has really driven us to care more about the oceans? If we go to the next slide, we have pivotal individuals I'd like to remind you of. And here is a friend and a colleague, Dr. Sylvia Earle, who really has conservation in every phrase that she utters: the love of the ocean, the care of the ocean, the concern for the ocean, and the need to conserve the ocean. So Sylvia Earle has really given us the component of passion to care about the ocean. And we have one component of society that understands that message: people who are ocean fans, ocean conservation fans, and they are profound and many. Next, then, I'd like to remind you of another remarkable figure, Dr. Jacques Cousteau, Captain Jacques Cousteau. And Captain Cousteau really brought generations of people to the oceans through the marvels of TV. Both happened somewhat simultaneously. As he became popular in the 60s and 70s, TV was introducing an outside world to the living rooms of many people, certainly America. Other parts of the world have caught up since, if their infrastructure was not enabling. But as Cousteau says, you can't save what you don't love, and you can't love something if you don't know of it. And that's really been his contribution among many, scuba diving among them. But Cousteau took us to a different level of just being able to see, touch, and believe we could be right there with Captain Cousteau, with Jean-Michel, with Falco and Philippe, and be part of these expeditions. It was a remarkable journey we could all take from our living rooms. Next, then, in a more contemporary sense, is Dr. Bob Ballard, who's also a partner of ours up in NOAA. And Bob's passion for exploration has been existing throughout his entire life. But he brings to us the excitement of discovery in the oceans, whether it's a deep sea hydrothermal vent that explains early life forms, or whether it's shipwrecks like the Bismarck or the Titanic, where epics of human history can be further revealed in undersea exploration. What is the key? What is the trigger? What will motivate the public to be looking back to the oceans and say, we must do something different than what we're doing today to the oceans? Will it be the passion of Sylvia Earle? Will it be the lessons of Cousteau to give us that immersion experience, or the modern immersion experience that Bob Ballard has delivered through telepresence, where we take imagery from the undersea and once again deliver it not to the living room televisions of the world so much as to your iPhone or your laptop, or to individuals enjoying the experience of excitement and discovery? That's an open question, but let's look a little bit further with the next slide, please. We know that the Earth is changing. We know that there are measurable and discrete phenomena taking place around us. We even know the causation. Let's look a little bit deeper. As we wire this planet in the next slide, we can see that these graphs give us the indications of the current earthly trends. Now, I know that geographers are very prominent in the recording of climes, microclimes, macro, global, and we know what the past history and variability has been in certain earthly areas. What we don't realize is that don't realize often enough, is that we can't use the past trends to forecast the future. We are abruptly changing those trends and causing a different outcome than what has been the normal variability in Earth's behavior, with the added insult of our change in the Earth's atmosphere and our change in the ocean, the physical ocean, the chemistry of the ocean, and the biology of the ocean. So our human influence is causing increased air temperature over the oceans, decreased snowfall, increased atmospheric humidity, decrease in sea ice, Arctic sea ice particularly. Ocean heat is going up at all depths, not just the surface ocean. Each of these gives us an indication of what's really changing in around the world. And when we realize that the 30% of Earth that we can see on a daily basis, which is the landmass, is having such a temperature change effect, we're not seeing on a daily basis what's happening in the oceans temperature change effect and how that's impacting the biology and the ecosystem of the ocean. These are matters that we should be concerned with. But let's go a little bit deeper. How do we know that these curves are verifiable? What is the activity we're undertaking in order to prove these or underscore these? Next slide, please. In NOAA and in many other federal agencies and academic communities, we're contributing to this understanding. We maintain the Global Observation Network for Greenhouse Gases. One side of this photo shows you our station at Mauna Loa, which is atop the second highest mountain or volcano, which has spiritual significance as well for the native Hawaiian population. We're monitoring Earth from this very spiritual and respectful place. And we also then take those samples and bring them into what's on the right-hand slide is Boulder, Colorado, where 24 hours a day, we're analyzing atmospheric greenhouse gas samples from around the world, including our principal observatories, one of which is Mauna Loa, one of which is in Barrow, Alaska, Antarctica, American Samoa, many other places. And then we also have samplers who are contributing to our collection. And these samplers make glass flask samples, put them in a Pelican case, and ship them to us for analysis in Boulder. And we get a signature of what the contemporary measurements are of greenhouse gases, many greenhouse gases, analyzed to parts per trillion in our laboratory in Boulder. So we're providing the definitional basis of what is happening in that global chemistry. And of course, air chemistry dissociates into ocean chemistry. So with the next slide, you can see that we use a number of technologies, and we try to cover as much of the Earth as we can with devices that you see in the upper right hand, which is an Argo float. An Argo float is a device that sinks down to 2,000 meters, makes measurements of conductivity, temperature, and depth. Conductivity then, combined with the other two attributes, gives us a salinity measurement. So we could look at the physical ocean with these devices in an automatic way, and after 10 days they come back up to the surface and they download their information by satellite. So we don't have to send oceanographic ships to all these locations that you see dotted on this map. This map represents the current distribution of these Argo floats in the world today. This is a project that the United States started, was joined by several other nations, but today we support, and NOAA in particular, supports 50% of these ocean observation tools that you see reported here. But take a look at the Arctic. If you look at this projection, you realize that the Arctic is really lean in its environmental coverage. Further, contemplate that the Arctic is the most rapidly changing part of the world today, and that our climate models are undervaluing the change in the Arctic. We need more observations in the Arctic, and we need more work in the Arctic. I like to joke, and it's not too much of a joke, but people much more enjoy tropical coral reefs, wetsuits, than bundling up with a parka and journeying to the Arctic or the polar regions for study. But we need to do more of that. You see some of the other technologies in this slide too that are adding to our ability, both by ships and automated platforms, whether they be mobile or sedentary, as you see in the slide here. Next slide, please. So the question then becomes, how much data are we collecting? And you can see right here from the polar orbiting and the geostationary satellites that NOAA operates every day in order to provide you with your weather forecast, in order to provide you with information about the movement of storms and other phenomena that we're measuring from space. But at 6.4 terabytes a daily download, that's an impressive amount of information. And we've engaged in partnerships with commercial players who will upload that information and then make it more easily accessible to the public, and also have the opportunity to balance a business model by selling at a very relatively low cost computation cycles. So researchers can gain access to this information very easily, either through us or through these commercial providers. But at 6.4 terabytes, you might be impressed with that. But try this. As we develop a model, for example, what I believe is the world's best climate model that we have coming from our laboratory in Princeton, New Jersey, the Geophysical Fluid Dynamics Laboratory of NOAA, 8 terabytes an hour generated in order to run and prove the effectiveness and excellence of a model, challenging it across centuries, simulated years of runs, changing attributes with each run. The volume of data that we are generating and that we have on record is huge. The point here is twofold. One is we've collected a lot and we've analyzed it, so we know a lot. The other point is with big data, there are many data sets that could be intersecting and give us even better visibility into what this future is going to look like as we start to think in terms of big data analysis. And we're very focused on that inside of our agency. Let's move now to, at a global scale, this confluence of priorities. With the next slide, please. We realize that the problems that I've alluded to here are captured not just in the reports and studies that I've identified for you, but I've also been captured in global ocean conversations at the Our Ocean series of conferences, which have taken place over the past 5+ years, at the UN Ocean Conference, at the Economist Group's Ocean Summits and the like. There are many other forums, but those forums continue to talk about largely these issues that you see on the left-hand side of the screen. These are compelling, these are necessary, and these are the challenges that we see in front of us. So let's look further. Let's add to Cousteau, let's add to Ballard, and let's add to Sylvia Earle with the next slide. What other motion is in play to deal with those priorities? The commercial community is realizing, whether it be banking and finance or individual business models, that the path we're on is not a sustainable one. Number one, it's not sustainable for planet Earth, as we see the impact and the forcing functions to constitute change in around the globe, but it's also not economically sustainable. We cannot produce products that have byproducts that harm the Earth. We need a circular economy. And the commercial sector, the people who sell you money to invest in a new business, the commercial sector is looking at this, and they're realizing that sustainable businesses are far more healthy and will be far more prosperous, not just during the term of the commercial paper that underpins them, but in terms of the quality of life that will be coming for all of us to enjoy. So transforming, whether it's to move from oil to renewables, as Europe is doing aggressively, and perhaps the United States will near term, but as we see these changes taking place, they're driven by policymakers and the makers of our economy and finance and investment industries by underscoring the wisdom of certain investments and the lack of wisdom of other investments. So I see a huge motivator coming here from the insight of the commercial sector and where funding is available or not for what type of technologies, and really moving towards a circular economy where the products of the economy are principally used, reused, repurposed, and the byproducts of that economy are not waste that's introduced to the environment, but they themselves have some use or capture technology to reuse them as well. Next slide, please. As we look at the COVID situation here, and I like this slide rather than showing the electron microscopy image of the virus itself. It's probably too familiar to us all. So with a little bit of a refresh, we just remind ourselves of wearing the mask, keeping socially distanced, and cleaning and washing our hands and the like, which are, according to the medical professionals, which I'm not one, but those are the practices I follow, and I hope you do as well. But in looking at what changes and what opportunities the COVID situation provides to us, there have been some enlightenments for us to realize that former economy, with the intercession of the COVID disruption, gives us a chance to build things better in the future, to redirect and redefine the way that our economy functions globally, as it will impact the ocean, as it will impact the distribution of people, and that which we know today in today's geography, which is probably not going to be similar to what tomorrow's geography looks like. Next slide, please. So where do we go with this? Well, I mentioned earlier the Intergovernmental Oceanographic Commission, and as a UN body, that IOC recommended that we take up a transformative opportunity featuring the oceans to really look at the ocean we need for the future we want. And this, ladies and gentlemen, is the UN Decade of Ocean Science for Sustainable Development. It will take place from 2021 to 2030. It kicks off January 1st. We're anticipating a celebratory event in Berlin, Germany, in the summer. That would be the formal kickoff of a hosted by the government of Germany and co-sponsored by the IOC, all the nations of the world coming together in order to really produce the type of science we need in order to inform society, enhance economies, conserve where appropriate, and then sustainably utilize the resources of the ocean. Let's see a little bit deeper where this takes us. Next slide, please. The Ocean Decade has set up several objectives, and we have 7 of these societal outcomes that we seek to achieve. These are largely self-explanatory, and appearing on the right-hand side of the screen are the additional UN sustainability objectives of the 2030 plan, which you can become more familiar with if you're not already, but they basically describe a more optimistic future for how we can treat planet Earth and the components and the benefits therefrom. But having a clean ocean without pollution, there are ways that we can stop pollution. We need science to explain that and find new pathways. Healthy and resilient ocean. We want to be able to rely on the quality of the ocean and not see coral bleaching or the demise of marine species around the world. We need to keep the ecosystem balanced, and that brings us to a productive ocean where we could sustainably harvest some of the components and feed the world's population. Next slide, please. Now we have the next 3, which would include a predicted ocean where our computing and observing come together, and we could forecast reliably, as I do believe our models do now, what the future will look like based on the observations we make today and based on historic observations that we can harvest, whether it be from paleo-based science or to just historic records that have been kept for the past several hundred years. A safe ocean. Anyone who's been on the ocean, or if you're as skillful as this surfer, you realize that people can get hurt in the ocean. So we can't really make the ocean itself safe, but we can give people warnings for what type of conduct or what type of proximity to the ocean they might make or take in investing in properties, in building constructions, or whether we swim during a high tide or high surf environment. So making the ocean safe, tsunami warnings, tropical cyclone warnings, this type of network is very important for us to completely cover the Earth with. And right now we do well, but we can do better, and that's one of the objectives we have. Okay, then an accessible ocean. Let's make the information available to everyone. Let's have a global community that exchanges information and makes nothing a secret, opens up everyone's databases and has it available through a common ocean portal. Now the next one I want to get to, and I'm reminded of what I offered you previously in terms of the excitement and discovery of the ocean, the last one of the 7. Next slide, please. An inspiring and engaging ocean. And here we bring you Moana, courtesy of the Disney folks, a brilliant film, which I love watching, whether I'm with my grandkids or not. And that is another element of what the ocean is about to us as humans. But it has tactical benefits, as you can see, indicated by those additional components of the UN 2030 agenda. So those are the 7 objectives that we seek to achieve. How are we going to do that? Next slide, please. We have roughly 10 initial ocean challenges. This will not be the totality of the UN Ocean Decade. This will be the beginning point of the Ocean Decade, where these priorities, and they'll match what you saw on that previous slide about the compelling issues that keep coming up at these international discussions about oceans. So this is what we plan to undertake for the first round of activity in the UN Decade of Ocean Science, through international cooperation, through a number of projects and programs that would span the globe. They will be both global, regional, sub-regional. They'll bring us to places and spaces that we haven't really seen before and give us answers to science questions and give us advice to policymakers and the makers of our global economy for how best to treat the planet Earth and reduce the trend that we're on of ocean change. So let's put this in perspective. Next slide, please. It's not long ago that we actually achieved the first captured image of giant squid, whether it be from the pages of Jules Verne to occasional samples that were dredged up from the ocean bottom. But to actually see one live was quite thrilling. And 2 research teams have really undertaken this successfully and brought back the results. So here are these great mysteries now available for us to see. Next slide, please. I get a kick out of these 2 slides. The one on the left is what we call a Dumbo octopus. It has the rather large, what appeared to be ear-like components. But if you look at the biology of the octopus, this fellow has curled up his 8 arms in a rounded way and is a much more hydrodynamic posture. And we marveled at this. We'd never seen this behavior from this octopus. Well, that's interesting. The octopus probably does this every day. We're just not there to see it. So the relative perspective of what we know about the ocean and ocean life is quite compelling. The one on the right I love, because we looked at that when we first saw it. We didn't even know what it was. So there are creatures in the ocean that we still don't know about. And I think that is remarkable. It's profound, but it's part of what we need to solve and settle, because both of these creatures have a place in the ecosystem. And you may think them inconsequential, but if you don't know what they do or how they do it, there is consequence to that lack of knowledge. One of the most recently discovered microbes is responsible for breaking down the components of algae, which produces our oxygen. And until those components are broken down and those nutrients reintroduced to the ocean environment, the next algal cell doesn't have those nutrients available to photosynthesize, metabolize, and produce oxygen. And we just discovered that in the past 20 years. That's not a long time. And we don't know what the behavior of this critter is. It's a microbe, actually. We don't know what the behavior of this critter is to ocean acidification or the other changes that we're watching happen now. There are a lot of vulnerabilities to changing an ecosystem, a global ecosystem, as fast as we are. And we need to understand that. Next slide, please. So the excitement to discover the ocean also brings us to the notion of marine spatial planning. We have to know what's out in the ocean. We have to map the ocean. We have to be able to map the physical, the biological, the archaeological. human history, and other notions, geological components of the ocean, in order to find the best utilization of these areas. That's upon us now. Europe, which would be better represented by the lower right-hand image, is far ahead of the United States, where we really only have one operational wind farm, very small footprint and very small activity right off of Rhode Island and Block Island. More coming. We have an experimental station that is up and running off of Virginia. More to come, but this is the future. We need to be ready for it. We need science in order to help drive the direction that we place and distribute these devices. Next, please. When we start looking at uncrewed ships, who's going to be in place to make the decisions that this transiting vessel needs to take into account in terms of moving that cargo safely? And the types of storms that ships pass through, we need better routing, better forecasts, and better ocean monitoring. Once again, the commercial interests will help drive this outcome for a more economic return that is sustainable, that doesn't damage the environment, and really delivers us to a better future. Now, next slide, please. The geography community is just champions, are champions as a whole of GIS. And really it's the level of representation of the information that geographers make their living on. And by bringing these large data sets into confluence with such tools as you see illustrated here is really going to be what many talk about as the next new blue economy. It's the value of the data that we have, how we represent it, how we convey it to the public. So your jobs are very important, that this changing ocean be quantified and documented and delivered at an understandable level to the public, but then further, that how it will change in a forecast be also documented, quantified, and capable of being delivered to the public. So I'll move to the last slide, if I can, please. Almost the last slide. The opportunities in our future are for us to look at the decade as a billboard. The fact that we have 150 nations of the IOC membership focused on supporting the UN decade, and over 190 nations in the UN as a whole supporting the UN decade, we're going to get something done here. And I think it's important for us to recognize, what do we need to know? How can we go about establishing a knowledge base in that area? How can we really be building our ambition, our readiness, and our use of this global attention to oceans to produce something better than what we have today? So I've got a few bullets on here that I think you can read for yourself, but basically it's hopefully a motivator. We need to be doing this work. We need to do it with more rigor and social understanding than we have today, and I think we have a huge opportunity to do so. I will look at the second to last bullet. When people ask about oceans and what we learn from the oceans, I say this often enough. It's been repeated on the floors of the World Meteorological Organization and also the Intergovernmental Oceanographic Commission. If you like your 7-day weather forecast, thank an oceanographer. Next slide, please. So into our future comes the opportunity of the U.S. Decade of Ocean Science for Sustainable Development. Please be thinking, what does your community need to know about the oceans? Generate those ideas into proposals for activities under the UN Decade. Work within your communities that you're both familiar with and new communities that you may today be unfamiliar with in order to find the basis and the means in order to go ahead and pursue these targets. There are many things that we can be doing differently. We need to. And from the science that we have today, we can draw many of the conclusions that we need for the future. But there still remains to be science. There still remains to be new discovery and interdisciplinary and ambitious science that could really bring the answers so that we could be defining the future that we want. So with the last slide, and I think now I have it right, the opportunity in our future is for you to get involved, to join, and to go on a journey different from the one you might have originally thought. This is a photograph of myself in an earlier characterization of my career when I was working on ships, piloting ships. I was the executive officer of the NOAA ship Albatross 4 here, later moved on to command ships. But it was a journey that I didn't think I was going to get to take when I was a young kid on that polluted river in the Passaic River of New Jersey. And many things happen to each of us. Let's make sure the things that happen to our grandkids are the ones that we want, the future we want for them. And frankly, ladies and gentlemen, that may not be the future we're headed for right now without a course change. Thank you very much.
Thanks, Craig, and we all wish you well as you continue to do great work over at NOAA. On behalf of everyone at AGS, thank you to the many organizations who make this symposium and the yearly work of AGS possible. We are especially grateful to all the organizations this year for providing your support, even though we cannot get together physically. Your recognition of the importance of continuing this multi-year strategic dialogue of the trends that will reshape the geography of our planet, be it in person or through technology, is important and necessary. AGS Chairman, Dr. Chris Tucker, has been interested in the ocean for a very long time and has thought deeply about what will happen to the ocean as the population of the planet continues to grow. Today, he has a very compelling lightning talk to let us know what is on his mind. Chris?
I'm here today to ask you to think about runaway population growth as a key part of the growing human footprint on our oceans. You might consider those two topics an odd combination. Certainly, no one really talks about the fate of our oceans in terms of the explosive growth in our human population. But in writing my recent book, A Planet of 3 Billion, I realized the burden humanity has foisted onto our oceans. Let me explain. For much of the past 120,000 years, humanity has tread rather lightly on our planet and our oceans. Until, say, 5,000 years ago, our impact was barely registered. 2,000 years ago, with 170 million humans on our planet, only a small proportion of humanity ever even saw an ocean during their lifetime. Most were farmers and herders far from the coast. They more likely heard stories about the oceans from travelers passing through their remote village. But over time, as humanity grew, we became an increasingly coastal species, increasingly reliant on the ocean for food, trade, exploration, colonization, war-making, and eventually vacationing and recreation. And as our numbers grew, our increasingly multifaceted relationship with the ocean came to resemble the modern ecological nightmare that it is today. Perhaps it's useful to step back and ask ourselves, how exactly should we think about this planet we are impacting? I like this biogeographical methodology for understanding the unique ecoregions that comprise our planet. Each represents unique constellations of flora and fauna, terrain, singular flows of water, and very specific climates. Each uniquely contributes to the ecoregions around them. And as humanity degrades the resources of each specific ecoregion, its impacts on the planet are quite unique and specific. Ecoregions are not just terrestrial. Marine ecoregions have been defined for every coastal marine environment around the world. This is not to say that deep ocean ecologies matter less, but it is easy to see how explosive growth in human population is impacting these ecoregions in a wide variety of ways. Worse and worse as we add 80 million additional humans to our planet each year. Just going back to the final frame of the earlier video for a moment, we can imagine how this runaway population growth, which is increasingly concentrated in coastal urban environments over the coming decades, will further burden our oceans. And if we map our human footprint by simply placing our human population in red, our road networks in gray, our intensive agricultural land in black, our toxic sites in purple, and our coastal dead zones in orange, just this handful of layers, we get a sense of how this population is deleting ecological resources, particularly in coastal environments, while excreting massive volumes of waste into our oceans. This spinning globe adds in yellow the massive continent-sized ocean garbage patches that humans have created only in the last century or so. What were once isolated industrial effluents from few major cities and the occasional cargo floating adrift in the ocean has fundamentally changed. With the dawn of plastics, only in the past century or so, this complex swirl of garbage has become an existential threat to our oceans and our ocean food chains. And it is only getting bigger as an ever larger human population creates ever more garbage that inevitably ends up in the ocean. And that does not even count the rest of these elements, the elements of our human footprint. Add to these coastal dead zones and continent-sized garbage patches the increasing acidification of our oceans as they absorb humanity's collective exhaust in the form of carbon dioxide. Also, we continue whaling at disturbing rates and killing 100 million sharks a year. We spew endocrine disruptors into the ocean, overfishing both illegally and legally. And as we move around our oceans, we help seed invasive species that in turn disrupt and promise to destroy our marine ecosystems. The oceans are dying because humans are killing them. And the rate of ocean die-off is accelerating, as we long ago blew past our planet's ecological carrying capacity. We continue deleting what ecological resources remain. And every day, we further burden the ever-decreasing volume of ecological resources that we still have left with the weight of humanity's persistent accumulating wastes. That's right, the oceans are dying because the humans are killing them. The ecological debt we've accumulated deepens every day, and will take generations to pay down even after we bring the global population down to our planet's actual carrying capacity. Yet, runaway population growth continues every day. To be clear, each additional human means more burden on our oceans, as we add more than 80 million humans to our planet each year. 80 million! Indeed, less consumption and more sustainable behaviors could help, and indeed, rich countries are disproportionately contributing to the death of the oceans. But the explosion in the size of the global middle class over the coming decades looms large in our ecological future. Yet, the bending of the global population curve is actually inevitable. The only question is when. A recent estimate in the journal Lancet had global population peaking at 9.7 billion in 2064, and then declining to 8 billion in 2100. That will mean adding as many as 2 billion more people than today, all placing additional burdens on our ocean. This article made it clear that because of women's empowerment, education, and access to family planning technologies are in effect ahead of schedule, the global population curve is bending ahead of the United Nations estimates. So, if this bending of the global population curve is already inevitable, why don't we invest more in women's empowerment, education, and access to family planning technologies in order to accelerate this already inevitable trend? Of course, women's empowerment is a good in and of itself and should be advanced in its own right. But apparently, it's also the key to unlocking a more sustainable future for our oceans and our planet. There are tons of things we can do to help humanity be less destructive on our oceans. The list is actually really long, but continuing to add 80 million additional humans to the planet every year, the equivalent of 10 New York cities, will continue to place additional pressure on our oceans that they simply cannot sustain. But if we targeted a global total fertility rate of 1.5 by 2030, we could begin to decrease the global population and reduce the pressure we're placing on our ocean ecologies. Maybe even make that target our 18th Sustainable Development Goal. Maybe the United Nations is listening. We can begin unwinding this terrible convergence of ecological disasters facing our oceans, and together, as small, educated, and prosperous families, think deliberately how we can craft a more sustainable future for our planet and our species, empower women, end runaway population growth, save our oceans, and together we can forge a more hopeful future.
Thanks, Chris. One of the leading foundations dedicated to the conservation, exploration, and education of the ocean is the Walter Munk Foundation. Today, we are very pleased to have Foundation President Mary Monk join us and talk about their work. Welcome, Mary.
Hello, I'm Mary Monk, president of the Walter Munk Foundation for the Oceans. We're so pleased to be part of this year's Geography 2050 conference focused on the future of the world oceans. We're excited not only to share a little information about the foundation and my husband Walter Munk's legacy, but how his 1947 paper on the Grand Canyons of La Jolla has led to the installation of the largest lithomosaic in the world, an educational, artistic map that tells the story of the underwater park and ecological reserves just offshore. We hope you will enjoy our story.
Off the California coast, there is a place of beauty, wonder, and adventure.
An underwater geographic wonder called the Grand Canyons of La Jolla.
The Grand Canyons of La Jolla are a geographical wonder. It's where you've got this canyon meeting this rocky shoreline. We've got kelp forests, rocky reefs, beautiful sand sort of canyons, and it's where the shoreline meets the deep ocean, and that's what makes it such a geographical wonder. And that's why it's also a state marine conservation area or marine protected area, and protected for the people of California and people everywhere because it's such a remarkable place.
It's a place so remarkable, so important to the future of the oceans, that a new piece of art has been dedicated here along its shoreline at La Jolla Shores Park. It's called The Map of the Grand Canyons of La Jolla.
The map brings the ecological wonderland of La Jolla Canyons to life in a way that so wonderfully merges art and education.
This map is a tiny component of the many things that we need to do for people to realize how much our societies depend on the oceans.
A creation of the Walter Munk Foundation, the map is fitted and formed from tiny tiles, 500,000 of them, pieced together into a magnificent mosaic marvel. But this map is not only a giant piece of art. Grab your phone or computer and the map becomes a high-tech gateway to the Grand Canyons of La Jolla and the more than 100 species of marine life that live here.
Each creature will have a QR code, so the community will be able to download the information on that species and learn all about the species that we have off our shoreline.
The marine life you're going to see on the map is controlled by the faults. The faults expose this rich tapestry of geology on the seafloor that the kelp can attach to, that the fish can live in and get shelter. So all of a sudden we have a link between what outcrops, what is on the seafloor, and what's the biohabitat. Furthermore, these canyons provide a conveyor belt of bringing nutrients and sand from shallow water to deep water. So this here affects habitats that are in the deep sea that don't ever see the light of day.
The tiles that do see the light of day may be small, but they are built upon the legacy of a giant, legendary oceanographer and foundation namesake, Walter Munk.
Professor Walter H. Munk is widely recognized as the world's greatest living oceanographer and the father of modern oceanography. He is the recipient of this year's Explorer's Medal.
Walter Munk walked our understanding of the system of oceans across a whole century.
So you look there and I look here? Okay.
From his boyhood home in Austria to the coast of his beloved Southern California, Dr. Walter Munk has changed the way we look at oceans. During World War II, he joined the Army and worked with the Navy. His studies of wind and waves helping our Allied forces turn the tides of battle.
He was leading the team that was figuring out the equations to predict the tides so that we could have a successful Allied victory in Normandy.
Over the years, he studied the effects on the ocean from nuclear blasts at Bikini Atoll to the waves that move us all.
Walter's early work successfully forecast the first ocean swells across the Pacific.
This had a huge impact and paved the way for surfers to be able to predict when and where to surf. He was the first surf forecaster, and we reap the benefits from him every day.
It was his work with swells here in La Jolla that in 1947 led Dr. Monk to publish a paper in the Journal of Geology on the refraction of ocean waves, linking underwater topography to beach erosion.
Dr. Monk had a great appreciation of these Grand Canyons off La Jolla, and he sketched what they would look like and how they would meander going down the slope. And other scientists were intrigued by his insights and followed up on these studies. These canyons here are fault controlled. So the Newport-Englewood-Rose Canyon fault comes up the 5, jogs to the west, comes across here by the beach and tennis club, and this fault controls the canyon head. The canyon head starts in about 8 meters of water, about 25 feet, and extends all the way down to about 1,200 meters, or 3,600 feet. Submarine canyons are canyons that are beneath the sea, and they scour the margins. So here, hidden from us, are mountains that are as high as anything we see here in Palomar Mountain, the lagunas. So these mountains and islands are because the topography offshore has been twisted and faulted and folded, and these faults control where the canyons are.
What's great about this map, of the big map of the Grand Canyon of La Jolla, is that it shows the open ocean linking it to the shoreline of these great species, and it has these lines. It shows these lines that come from a paper from Walter Monk in the 1940s that show the bathymetry, the currents, the wave refraction here that make this such a special place, as well as marking the marine reserve. So it's really, really an amazing piece of geography in action.
It is geography that has come to life. A map that not only stands as a gateway to these unique underwater canyons, but now welcomes the next wave of explorers toward the future of our oceans.
This map is going to give insights and trigger curiosity in the scientists to come. So these maps and these renditions that represent the Grand Canyons of La Jolla will spark new frontiers of research.
It will inspire, educate, and provide access to our local ecological and geological wonderland to all the people of San Diego and many visitors from all over the world for years to come.
Thank you, Mary, and we look forward to the many projects the Monk Foundation will be spearheading in the future. Once the COVID-19 pandemic began, it wasn't long before we realized we would have to make alternative plans for our symposium. We knew we would not be able to gather in New York City in November and wondered how we could improvise. We spent weeks looking for ideas, and it wasn't long before we noticed a unique website and got to know the person behind it and thought, you know, this might be the way to hold the symposium through the use of technology. When we approached Adam Simmons over at Geospatial Frontier, we didn't even have to finish our sales pitch to ask him to help us before he immediately offered to partner with AGS. Thank you, Adam, and Project Geospatial for making this possible. So that concludes our first day of the symposium. Don't forget, we start tomorrow with a new theme and all new presentations. See you then.